Every second, billions of bits of data are flying across the bottom of the Atlantic Ocean in like pitch black fiber optic cables.
Yeah, and right now the universe, through microscopic fluctuations in heat, cosmic rays, and just general quantum noise, is actively trying to scramble them.
Right, which is wild to think about. So today we're looking at the exact mathematics of how we fight back against that.
Because without relentless, highly advanced error correction operating at the physical layer, I mean, the digital world you rely on simply collapses into static.
It really does.
We like to think of data transmission as a clean, guaranteed pipe. You send a picture, you receive a picture. But the physical reality is profoundly messy. The signals are basically probabilistic ghosts.
Which brings us to the mission of this deep dive. If you design hardware or work in telecommunications, this material is going to fundamentally change how you view silicon efficiency. So, we are initiating the unabridged protocol. Our target for you today is a rigorous, completely unconstrained deconstruction of the paper Chase-like Decoding, Test Pattern Design, and Performance Analysis.
Right, by Tim Janz, Simon Obermüller, Andreas Zunker, and Stephan Brink from the University of Stuttgart.
Yes.
It is a phenomenal piece of mathematical architecture.
Yeah.
I mean, they are tackling the absolute bleeding edge of forward error correction for high-speed optics.
They really are. And because we are under the unabridged protocol, let me just state the parameters explicitly for you listening.
Please do.
There is only linear progression here. We start at the abstract, we end at the final mathematical appendix. There is zero illusion of time constraints. We are going to just sit with this material until it gives up its secrets.
Exactly.
And critically, to ensure no nuance is left behind, we will be conducting completeness checks after every single major section or complex formula.
Right, because that is the only way to truly respect the density of what the authors have built.
Right.
If we skip the foundational math, well, the final result just loses its weight.
Exactly. So we begin at the abstract. Sentence 1. Chase-like decoding algorithms are a popular choice for soft input decoding of algebraic codes. I want to pause immediately. Let's not patronize anyone with a basic definition of binary, but physically, in the silicon, what is the hard difference between soft input decoding and hard decision decoding?
Right, so in a hard decision system, the receiver's hardware looks at a fluctuating analog signal, like a voltage wave or a pulse of light.
Okay.
And a simple comparator circuit just draws a rigid line. Above a certain voltage threshold is a 1. Below is a 0. It completely strips away all the analog nuance.
So it's like grading a test, strictly pass or fail.
Exactly. But a soft input decoder, which this paper focuses on, preserves the reliability of that signal.
Oh, I see.
Yeah, if the voltage is hovering right on the threshold line, the analog to digital converter doesn't just flip a coin. It passes along the bit, but tags it with a low confidence score.
So the decoder knows it's essentially looking at a coin flip.
Right. And Chase-like decoding algorithms use those statistical confidence percentages to make incredibly smart guesses about where errors are most likely to have occurred in the data stream.
That makes a lot of sense. Moving to sentences 2 and 3 of the abstract.
Okay.
The authors state they are evaluating the performance of different test pattern sets using 3 distinct methods: order statistics, covered space probabilities, and Monte Carlo simulation. Why lean on these 3 specific lenses? Like, why not just use one?
Well, because relying on just one is dangerous when you are designing at this scale. Monte Carlo simulation is brute force. You simulate billions of noisy transmissions and simply count the errors that slip through.
Right.
It's undeniable, but it's computationally agonizing for low error rates. Then covered space probability is more of a geometric approach.
How so?
It maps the mathematical volume of possible errors your algorithm successfully anticipates. And finally, order statistics is the elegant but brutally complex analytical approach. It deals with the mathematics of sorted random variables. Because the hardware physically sorts incoming bits from least reliable to most reliable, the underlying probability distributions warp significantly.
Wow. Okay.
So the authors are setting out to prove that all 3 of these entirely different mathematical lenses converge on the exact same truth.
That's fascinating. And the final sentence of the abstract delivers the punchline, right? They propose a new test pattern design algorithm that performs up to a certain gain better for high-rate BCH codes.
Yes, the performance gain is stated mathematically as $0.22 decibels, 0.2 decibels.
Okay, a lot of people might look at 0.2 decibels and think, well, who cares?
Right, sounds tiny.
Yeah, it sounds like turning the volume dial on your stereo a microscopic fraction of a millimeter. But physically, in a hyperscale data center, Why does this fraction of a decibel matter so much?
To a hardware engineer, zero point 0.2 decibels is massive. Yeah. In telecommunications, signal-to-noise ratio, or SNR, is measured logarithmically. Achieving the exact same error rate while allowing the physical signal to be zero point 0.2 decibels noisier fundamentally changes the physics of your hardware.
Wait, how does it change the physics?
Well, it means you can use a cheaper, lower-power laser to drive the fiber. It means your silicon chip generates less thermal heat, which is, the absolute bottleneck in modern data centers.
Oh, wow.
In a transoceanic cable, that 0.2 dB margin might mean you can physically place your expensive underwater repeater stations miles further apart.
So it's not just a math trick. It's capital expenditure. It's real money.
Absolutely.
Okay, that covers the abstract.
Yeah.
So we need to execute our first check. Before we dive into the background, are there any nuances in their opening claim we missed?
I don't think so. The foundational claim is clear. They are promising better performance for high-rate codes using a novel pattern design. I think we're thoroughly primed to proceed to the introduction and see exactly what codes they are targeting.
Perfect. Section 1, Introduction. Paragraph 1 introduces Bose Hocquenghem codes, or BCH codes.
Right.
The authors know their good minimum distance and efficient decodability, making them widely used in communication systems, especially concatenated schemes like data center interconnects using the KP4 504,514 Reed-Solomon code, and long-haul optical communication schemes like OAV.
Yeah, the Open Forward Error Correction Standard.
Exactly. We know you listening are familiar with standard error corrections, so let's bypass the deep history lesson. But why are high-rate BCH codes the specific battleground here? Like, why not LDPC or polar codes?
It really comes down to latency and hardware complexity. Concatenated schemes use 2 layers of armor.
Okay, 2 layers.
You have an inner code that touches the raw, noisy physical channel, and an outer code like the Reed-Solomon code they mentioned that sweeps up whatever leaks through.
Got it.
For a standard like AVC, which is the protocol for pushing 400 gigabits per second and beyond, you simply cannot afford the latency of a massive, iterative LDPC decoder for the intercode.
It's just too slow.
Way too slow. BCH codes are algebraic. They use finite field mathematics to compute syndromes in a deterministic, incredibly fast number of clock cycles.
Oh, I see.
They are the gold standard when you need to process billions of bits per second without holding the data in a massive memory buffer.
Which sets up the core problem in paragraph 2 perfectly. There is a performance gap between hard decision decoding using a bounded distance decoder, a BDD, and maximum likelihood, or ML, performance.
Right.
Let's look at the mechanism here. A BDD draws a rigid geometric sphere around a received message.
Exactly, a Hamming ball.
Right. If the true message is inside that sphere, it corrects it perfectly. If the noise pushes the message outside that sphere, it just fails. Whereas maximum likelihood evaluates every single possible code word to find the best match. But ML is computationally impossible for long codes, right? Like you'd literally melt the silicon trying to check every combination.
You absolutely would. For a 256-bit code, an ML decoder would have to check 2 to the power of 256 possibilities for every single incoming message.
That's absurd.
It is. So we need a bridge between the blind rigidity of the BDD and the impossible perfection of ML.
Which paragraph 3 introduces, right? The Chase-2 algorithm.
Yes.
The paper states that for a given channel output, it generates a list of candidate code words by decoding a specific number of test words. And the number of test words is 2 p-ballers to the power of p.
Exactly.
How does the hardware actually execute this, practically speaking?
Well, the hardware physically isolates the least reliable bits in the received block. So if p equals 4, that's 2 to the 4th, or 16 possible combinations of 1s and 0s for those sketching bits.
Okay, 16 combinations.
The silicon literally spawns 16 parallel tracks. It flips those unreliable bits through all 16 variations, feeds all 16 variations into 16 parallel bounded distance decoders, and sees which one spits out a valid code word.
So it's an elegant brute force hack localized just to the weakest links.
That's a great way to put it, yeah.
But paragraph 3 doesn't stop there. It mentions GRAND-D, which is guessing random additive noise decoding, and something called logistic weight patterns.
Right, GRAND flips the entire paradigm. Instead of trying to decode the message, it tries to guess the noise.
Like asking, what is the most likely error the universe just threw at us?
Precisely. And logistic weight is a mathematical framework for ordering those guesses. If you sort the bits by reliability, you can assign a mathematical weight to an error pattern.
Okay, how does the weight work?
Flipping a highly unreliable bit costs a small penalty. Flipping a highly reliable bit costs a massive penalty. This allows the hardware to prioritize testing the most mathematically probable error geometries first.
That makes total sense. And this leads right into paragraphs 4 and 5. The authors identify a gap in the literature, a lack of thorough comparison of these different sets of test patterns, especially for the high-rate BCH codes used in modern optical standards. Their roadmap is to present 3 methods to determine the list error rate: the LER, which is the probability that the correct code word wasn't even in the generated list, and then propose their new 0.2 dB gain algorithm. So before we move into the heavy math preliminaries, let's execute a check. Are we clear on the physical problem they are solving here? Have we missed anything?
We've established the bottleneck perfectly. High-speed optics demand fast, algebraic BCH codes. Hard decision BDD is too weight. Maximum likelihood is too slow. Chase-like decoding is the necessary bridge, but generating the optimal test patterns for that bridge is an unsolved problem. We are fully primed for the mathematics.
Let's do it then. Section 2, preliminaries. We are entering the mathematical notation phase. This is really the bedrock of their argument.
It is.
First, they define index sets. $1 triangle Opla, the set n is defined as the integers from 1 to n.
Yep.
And BR m plus 1, the set m to n is defined as the integers from m to n. Next, they define the power set. The notation is mathcal pk, the power set script p subscript k.
Right.
We don't need to define what a basic power set is for you listening, but why is restricting the power set so vital to the actual hardware design?
Because the power set represents combinatorial explosion. If k is the set of index positions for your least reliable bits, script p subscript k is every possible combination of bit flips across those positions.
Okay.
If you look at just 10 bits, the power set is 1,024 test patterns. That requires 1,024 parallel decoding circuits in your silicon. Hardware real estate is finite.
Right, you can't just build an infinitely large chip.
Exactly. The entire game of this paper is figuring out how to severely restrict our selection from that power set without sacrificing our error-catching capability.
Next is the vector space definition. MathUBF, 2NF for air, the vector space F2 to the n, and a subvector definition, VK emis subscript k in F2 to the cardinality of k, then an indicator vector, 1 to all the indicator vector 1 subscript k. This is just a string of length n with ones exactly at the positions in the set k and zeros everywhere else.
Right.
How does the hardware use an indicator vector physically? Like, what does it do?
It acts as an error mask. In the logic gates, you take your received message and you apply an XOR operation against this indicator vector.
Okay, an XOR gate.
Yeah. Wherever the mask has a 1, it physically toggles the voltage state of that specific bit in the message, flipping a 0 to a 1 or a 1 to a 0. It's the literal mechanism of injecting our test patterns into the data.
Which brings us directly to the addition operator, $1 plus v, 1 plus v, the element-wise addition over F2.
Right, the modulo 2 addition, the XOR gate. It's the fundamental arithmetic engine of the decoder.
Then we have weight and distance, the Hamming weight, below you subscript h of u, the Hamming weight, Hamming it, subscript h of u, comma v, the Hamming distance.
In binary space, Hamming distance isn't like physical distance. It's strictly the number of bit positions where 2 sequences differ.
Right.
If I send 1,000 and you receive 101, the Hamming distance is 2. The geometry here is entirely discrete.
Which introduces the beautiful geometric concept they rely on, the Hamming ball. The definition is math olnis v. The Hamming ball script b subscript r of u is defined as the set of vectors v in F2 to the n such that the Hamming distance between u and v is less than or equal to r.
Yes.
I find visualizing this really fascinating. Instead of a sphere in 3D space, it's a sphere in an n-dimensional hypercube. How does this dictate the decoder's behavior?
Well, think of a valid code word as a single anchor point in a vast multidimensional grid. The bounded distance decoder, the BDD we keep mentioning, draws a Hamming ball of radius r around that anchor point.
Okay.
It programs the silicon to say, I claim absolute ownership of any point within a distance of r bit flips. If a noisy message lands anywhere inside that geometric ball, the decoder's logic gates immediately pull it down to the center anchor point, correcting the error perfectly.
And if it lands outside?
If it lands outside, the decoder cannot resolve it. It just fails.
Got it. Finally, for this section, the logistic weight. The formula is sum I 1 I u. The logistic weight, w subscript L of u equals the sum from I equals 1 to n of I times u subscript I.
Right.
I want to push back on this a little bit. I understand we are summing up the bits u subscript I and multiplying by the position index I. And I know the incoming bits are sorted by reliability, so position 1 is the sketchiest bit.
Mm-hmm.
But is this linear penalty, just multiplying by I, actually a rigorous mathematical proxy for probability, or is it just a convenient engineering heuristic?
It's an astoundingly tight heuristic born from the physics of the channel.
Oh, really?
Yeah, the paper's authors and the broader literature on Grand have proven that under a Gaussian noise model, the logistic weight perfectly orders the most likely error patterns for high signal-to-noise ratios. It avoids complex floating point probability calculations completely.
So it's super efficient.
Exactly. If you flip bit number 1, it adds 1 to your weight. If you flip bit 50, it adds 50. It heavily penalizes assuming an error happened in a reliable position. The hardware can calculate a simple integer sum in a single clock cycle. It's brilliant.
Okay, before we move to the channel model, time for completeness check. Are there any assumptions in these preliminary definitions that we glossed over? Have we unpacked it thoroughly?
I think we're solid. We
Wow.
established the XOR masking, the hypercube geometry of the Hamming balls, and the integer logic of the logistic weight. The mathematical vocabulary is fully locked in. Let's look at the physics of the noise.
Okay, subsection 2IA, channel model. We are looking at a line-by-line deconstruction of the BIA-WGN channel, which is binary input additive white Gaussian noise.
Right.
The output is defined as $y x plus z d, y equals x plus z, the channel output. The noise is defined strictly. Z sim math cal in 0, sigma 2 0, is distributed as a normal distribution with mean 0 and variance sigma squared.
This represents the physical wire or the fiber itself. X is the clean signal we transmit. Z is the thermal and quantum chaos the universe injects.
And why?
And Y is the corrupted voltage we actually measure at the receiver. The variance, sigma squared, represents the absolute power of the noise.
Makes sense. The mapping is BPSK. $0 maps to plus 1 n over 1 n over 0 maps to plus 1 n 1 maps to minus 1, the BPSK mapping.
Why are we shifting zeros and ones into positive and negative domains?
Because you can't transmit an abstract mathematical integer over a copper wire or an optical phase modulator. You have to translate it into physical energy.
Right.
A positive one means driving a positive voltage or a specific phase of a laser. A negative one is the opposite phase. This gives the analog receiver two distinctly opposite physical states to differentiate.
Got it. Then the error correction capability of the code is defined as d hel floor, frac d min tel floor, t equals the floor of d sub min minus 1 over 2. This is the radius of those Hamming balls we discussed earlier. D sub min is the minimum distance between any two valid code words in the entire mathematical structure.
So if the two closest code words are, say, 7 steps apart,
Then you can safely program the hardware to draw a ball of radius 3 around each of them, and those spheres will never mathematically overlap. The floor function just rounds down to the nearest whole integer, so the code guarantees it can fix up to 2 errors perfectly.
now we get to the soft inputs, the log likelihood ratio. The log likelihood ratio, L equals 2 divided by sigma squared times y. Okay, physically, how does calculating a logarithm help the silicon? Like, why do engineers universally prefer log likelihoods over raw probabilities?
Imagine your hardware is trying to calculate the combined probability of 20 independent events, each with a 10% probability. You have to multiply 0.1 times 0.1 20 times.
That's a lot of tiny numbers.
Exactly.
Yeah.
In Silicon Logic, multiplying fractions rapidly leads to floating point underflow. The numbers get so small the computer rounds them to absolute zero, totally destroying the data.
Oh, wow.
But mathematics gives us a loophole. The logarithm of a product is the sum of the logarithms. By working in the log domain, complex multiplication circuits are replaced by simple, blazingly fast addition circuits.
That is so smart.
Yeah, the LLR cleanly wraps the hard decision, which is the positive or negative sign, and the soft confidence, the magnitude, into a single, easily manipulated number.
Which directly gives us the reliability definition. Alpha is defined as the absolute value of L. And the crucial assumption, the received channel output is already sorted such that alpha 1 null alpha 2 dots, alpha and alpha 1 is less than or equal to alpha 2, and so on up to alpha n.
Right.
I have to ask, sorting an array of 256 or 512 analog values in real time at billions of bits per second, isn't that physically incredibly demanding for the hardware?
It is extremely demanding. Real-time sorting architectures use complex pipeline networks, like bitonic sorters, that consume a massive amount of silicon area.
Yeah, that sounds huge.
This is precisely why the authors are fighting to minimize the number of test patterns. The sorting alone eats up a huge portion of their power budget, so the subsequent chase decoding step must be as efficient as mathematically possible.
The error vector is then defined as E a plus hattie. The error vector E equals CO plus Y hat. C is the true code word. Y hat is our hard decision guess. The XOR operation spits out a 1 exactly where our guess was wrong. Now we arrive at equation 1. This calculates the probability that the hard decision is erroneous at exactly B positions. BPE BQ1 sigma, BQ1 sigma. The probability of event E sub B equals N, choose B, times 1 minus Q of 1 over sigma to the power of B times Q of 1 over sigma to the power of N minus B.
Right.
This is a binomial distribution, but let's break down the mechanics physically. How does this map to the errors actually hitting our fiber?
The Q function is the tail probability of the Gaussian noise bell curve.
Okay.
So Q of 1 over sigma is the physical likelihood that a massive voltage spike flips a specific single bit. And Q of 1 over sigma to the power of N minus B is the probability that N minus B specific bits survive the channel completely unscathed. Conversely, 1 minus Q of 1 over sigma is the probability that a bit is destroyed. We raise that to the power of B to find the probability of exactly B bits being destroyed.
And what about the binomial coefficient at the front, the N choose B?
We don't just care about a specific set of B errors. We care about any combination of B errors anywhere in the N-bit block.
Wow, right.
N choose B calculates the sheer combinatorial volume of those arrangements. Multiply that volume by the individual probability and you get the total probability of exactly B errors occurring anywhere in the frame.
Which makes equation 2 perfectly intuitive then. The probability that a standard bounded distance decoder succeeds, PBDTEO-250, the probability of bounded distance decoding equals the sum from I equals 0 to T of the probability of E sub I.
Right. Since the decoder can fix up to T errors, its overall success rate is just the cumulative sum. The probability of getting 0 errors plus the probability of getting exactly 1 error plus 2 all the way up to T.
And beyond T?
Anything beyond T, the basic decoder catastrophically fails.
Completeness check time. Have we missed any physical implications in the channel model before moving to the chase mechanics?
The translation from Gaussian noise to log likelihood ratios and binomial probabilities is fully established. I'd say the foundation is rock solid. Let's look at how chase attempts to extend that BDD probability.
Great. Subsections IB and IC, chase-like decoding and covered space. The generalized chase algorithm generates its test words with this formula. The generalized chase algorithm generates its test words with this formula. The set of test word script T equals the set of Y hat O plus rho, such that rho is in the set of test pattern script R. Let's dissect the difference between the standard chase2 set, script R subscript chase, and the restricted set, script R subscript res.
We noted earlier that standard chase ESIC, it takes the T least reliable bits and generates every possible combination. If P equals 8, it generates 2 to the 8th, or 256 test patterns.
Right.
But the restricted chase script R subscript res introduces a governor W max-H, the maximum Hamming weight.
Wait, why restrict the weight? Why deliberately choose to ignore potential error patterns?
Because the physics of noise dictates that probabilities drop off a cliff. The chance of the noise perfectly targeting and flipping 8 specific bits simultaneously is vanishingly small.
Oh, I see.
The restricted chase acknowledges this reality. It says, we will look at the 8 least reliable bits, but we will only generate patterns that flip a maximum of 3 bits. You might cut your pattern list down from 256 to 93.
That's a huge reduction.
It is. You save 163 parallel decoding circuits in your silicon, which is massive power savings, and you mathematically lose almost 0 error correcting capability because the 163 patterns you threw away were statistically virtually impossible anyway.
That is brilliantly pragmatic, and this logic bleeds perfectly into definition 1, logistic weight patterns.
Yes, it does.
They define the set script R subscript LW. They state that for a set size Q, they choose the Q patterns with the absolute smallest logistic weight, but they implement strict tie-breaking rules.
Very strict.
Right. If 2 patterns have the same logistic weight, they first choose the pattern with the smaller Hamming weight. If they are still tied, they choose the pattern with the smaller binary representation. Why are ties so critical to handle mathematically? Does the hardware actually care?
The hardware absolutely cares about determinism. If your decoder encounters a tie and randomly picks between 2 paths, you cannot guarantee a minimum performance threshold, and you cannot rigorously mathematically prove your system works.
That makes sense.
Furthermore, prioritizing a smaller Hamming weight is deeply physical. If 2 error geometries are deemed equally likely based on reliability scores, the universe fundamentally prefers the one requiring less overall noise energy, which means fewer total bit flips.
Moving to subsection IC, they present a critical decomposition of the list error rate, P-Maskell C. plus p math LC. The probability that c hat does not equal c is less than or equal to the probability of ML error plus the list error rate. I love this inequality because it cleanly separates the blame when the system fails.
Exactly. The total probability of catastrophic failure is split into two distinct physical causes.
Right.
The first term is the maximum likelihood error. This represents the fundamental, unavoidable limitation of the mathematical code itself. If a monstrous noise spike mutates the message so perfectly that it looks exactly like a different valid code word, not even an infinite computer could save you.
Wow. And the second term?
The second term is the list error rate. This is the failure of the engineer. It means the true code word was theoretically discoverable, but your specific set of test patterns simply didn't cast a wide enough net to find it.
So the entire goal of this paper is shrinking that second term.
Precise.
Which brings us to the geometric heart of the paper in ID covered space. Equation 3 defines the covered space geometry. MathKill V, the covered space script V, equals the union over rho in script R of the Hamming ball of radius t around rho. Let's visualize this.
Go back to our hypercube. Every single test pattern row you generate acts as a brand new anchor point in that dark, multi-dimensional space.
Okay.
From every one of those new anchor points, the hardware projects a Hamming ball of radius t. The covered space script V is the massive, lumpy, overlapping union of all those individual spheres. It represents the total mathematical volume your algorithm is actively scanning.
Equation 5 calculates the exact probability of that space. Pethy probability of the covered space P subcov of Y equals the sum over V in script V of the probability of V given Y. If the true error vector falls anywhere inside that lumpy geometry, the decoder catches it. If the error falls in the dark space outside, the system fails.
Precisely. The covered space is the literal physical footprint of your algorithm's effectiveness.
Before we move on to evaluating these methods, completeness check. Are we solid on the geometric visualization of covered space and the physical necessity of restricted weights? Have we fully unpacked this section?
The hypercube geometry is fully mapped, and the hardware logic for restricting subsets is totally sound. We are clear to move to Section 3.
Let's do it. Section 3, Performance Evaluation Methods. The authors state they will unpack the math behind the three methods they introduced earlier, but first, they define a crucial metric, the marginal benefit of adding a single test pattern.
P sub add script R of rho is defined as the probability given the set script R union rho that C is in L minus the probability given script R that C is in L. So this literally calculates if I spend the silicon real estate to add one more test pattern circuit, exactly how much does my overall success probability increase?
It is the mathematical definition of return on investment. If P sub add is high, that pattern explores entirely new, highly probable territory in the hypercube.
And if slow?
If it's near zero, that pattern is entirely redundant. It's exploring space you already mapped.
Subsection A, list error rate with order statistics. Here we really enter the heavy math.
We do.
They introduce property 1 for logistic weight patterns. They state that for a fixed pattern row, all patterns with non-zero positions that are a subset of rows' positions are also naturally included in the set. The authors casually mention this coincides with a useful hardware trick. What trick?
It's about computing syndromes. Decoding a BCH code requires heavy polynomial arithmetic to check for errors. If your next test pattern is completely random, you have to recalculate the massive polynomial from scratch.
That sounds computationally expensive.
Very. But if your next test pattern only differs from your previous one by a single bit flip, which property 1 naturally encourages, you don't start over.
You take the previous result, XOR, the mathematical contribution of that single flipped bit, and you have your new syndrome instantly. It saves an immense number of clock cycles.
That is so clever. Then we hit lemma 1, which states that for an ordered set of logistic weight patterns, the newly covered error vectors from adding pattern row sub key are explicitly definable based on a maximum index position IMAX. We will trace the rigorous proof of this later in Appendix A, but this leads directly to the core analytical engine. Proposition 1.
Right.
Let's look at equation 9. Sum I max, sum I plus sum I max C at the probability of P sub delta that C is in L equals the sum from I equals 0 to T of the probability of E sub I plus the sum from I equals 1 to W max H of the sum over rho in script R sub I of the probability that E evaluated at I max rho equals rho evaluated at I max rho given E sub T plus I times the probability of E sub T plus I. This is visually a monster. Can we explain how the induction proof proves this actually works? An induction proof works like a chain of dominoes. You prove the first domino falls, and then you prove mathematically that if any domino falls, the one next to it is guaranteed to fall.
Okay, so what's the first domino here?
They start with the base case, a decoder with only one pattern, the all-zero pattern. In that case, the probability of success is simply the first term of the equation, the basic BDD formula we saw earlier. The first domino falls.
Right.
Then they say, assume the formula perfectly calculates the probability for Q patterns. What happens when we add the Q plus 1 pattern?
That's where lemma 1 comes in. Right.
Exactly. Lemma 1 dictates exactly what new, unique geometric volume that new pattern covers without double counting overlapping spheres. That massive double summation in equation 9 is simply iterating through every single pattern and calculating the conditional probability that the actual channel noise perfectly matches our test pattern up to that critical index position.
Wow.
It mathematically proves that you can analytically stack the probabilities of these geometries perfectly.
Moving to method B, the covered space approach. Equation 10 uses a Monte Carlo simulation over the space of received vectors, y. The expected value over y of p subcov of y is approximately 1 over n times the sum from I equals 1 to n of the sum over v, in script v, of the probability of v given y.
This relies on the law of large numbers. Instead of doing the agonizing analytical math of order statistics, you just blast the software simulation with n random noise realizations.
Right, brute force.
Yeah, for each realization, you calculate the probability of the entire covered space script v and average them all together. If n is large enough, your approximation converges to the theoretical truth.
And method C is the direct Monte Carlo simulation. The paper states this is the straightforward way. Physically simulate the transmission, run the full chase algorithm, and check if the code word is found. But they note it becomes computationally prohibitive for high SNRs.
Extremely prohibitive. If you are operating at an optical SNR where an error only occurs once in every trillion transmissions, you have to simulate trillions of entire data frames just to observe a handful of errors.
So you're basically waiting forever.
You are. It requires server farms running for weeks just to generate one single data point on a graph.
Completeness check on section 3. We've covered the marginal benefit logic, the induction proof structure for order statistics, and the Monte Carlo limits. Are there any loose ends we need to tie up?
I think the mathematical evaluation frameworks are fully established. We know how to measure success now, so we can proceed to section 4 to see how they actually design the test patterns to maximize that success.
Section 4. Pattern designs for chase-like decoding. This is where the authors pivot from analyzing existing methods to creating something radically new. They define the optimal set of patterns as script R subscript opt, but they immediately drop a bomb. Finding script R subscript opt is NP-hard.
Yeah, they do.
Why is maximizing a submodular set function an NP-hard problem? Why can't we just solve it?
NP-hard is computer science terminology for computationally intractable. When you are trying to find the absolute perfect combination of test patterns, the variables interact dynamically.
Dynamically how?
If I pick test pattern A, it covers a certain geometric volume. If I then consider pattern B, its mathematical value depends entirely on how much its volume overlaps with pattern A. The function is submodular, meaning there are diminishing returns based on what you already chose.
I get it.
Because these spheres overlap in such complex multidimensional ways, there is no shortcut algebraic formula to find the best set. The only way to guarantee you found the absolute optimal set is an exhaustive search, checking every single possible combination.
Which we establish is impossible.
Right. For a block length of 256 bits, the number of combinations vastly exceeds the number of atoms in the observable universe.
So exhaustive search is dead. They have to find heuristics.
Yeah.
Clever approximations. First, they discuss OCP, ordered candidate patterns. They algorithmically order the full space according to the probability of the Hamming ball. Then they discuss a greedy pattern design. How does a greedy algorithm function here, and why is it still too expensive?
A greedy algorithm looks at the problem one step at a time and makes the best immediate choice without looking ahead. So for the first pattern, it scans the entire universe of possibilities and picks the one that covers the absolute most probability. It locks that in.
Okay.
For the second pattern, it scans everything again and picks the one that adds the most new probability, specifically ignoring the overlap with the first pattern. It repeats this until it has Q patterns.
That sounds reasonable.
Mathematically, it is proving to be the best possible polynomial time approximation for this kind of problem. But here's the catch. Even scanning everything step by step is brutally slow for long optical code lengths because the search space of individual patterns is still 2 to the n.
Which brings us to the author's novel contribution. Subsection C, Maximum Covering Pattern Design, or MCOC, they present Algorithm 1. We are going to do a line-by-line reading of this pseudocode because this is the 0.2 dv breakthrough.
Let's do it.
Line 1. Initialize the set script R as empty. Set index I to 1.
While the size of script R is less than Q, execute the following loop.
Set row to be the ith most likely candidate pattern from OCP.
This is the critical IF statement. The logic is, in math call T key TH, the minimum over row prime in script R of the Hamming distance between row and row prime is strictly greater than TT. I want to stop exactly here. Why do we skip candidate patterns that are already within distance T of an existing pattern in our set?
This line of code is the absolute stroke of genius in the heuristic. Remember the Hamming balls. Every test pattern we choose gets a sphere of radius T drawn around it by the hardware decoder.
Right, the geometric spheres.
If we look at a new candidate pattern and its geometric distance to a pattern we already selected is less than or equal to T, it means this new pattern physically sits inside the sphere of the old pattern.
Oh.
It will catch almost the exact same errors. It is utterly redundant. The algorithm checks this condition instantly. If the distance check fails, the algorithm immediately throws the pattern out without doing any heavy probability calculations.
So it's geometric pruning. It's pruning the search tree based on physical distance rather than math.
Exactly.
Continuing the algorithm, lines 5 through 8, if the pattern passes that distance check, the algorithm then searches locally around that candidate to find the absolute most probable individual error vector within its own sphere and adds that highly optimized vector to the set script R.
Break the local search and move to line 13.
Increment I by 1 and repeat the while loop until Q patterns are found.
Return the optimized set script R. I'm looking at this, and it feels like a phenomenal blend of the greedy philosophy and geometric pruning.
It is. It dodges the NP-hard exhaustive search, it dramatically accelerates the greedy search by immediately throwing out overlapping spheres, and it centers its final choices on the highest probability vectors. It's an elegant, highly practical engineering solution to an intractable mathematical problem.
Completeness check on section 4. Have we fully verified the NP-hard limitations and the pruning logic of the MCOC pseudocode? Did we leave anything out?
The algorithmic logic is completely traced. The core mechanic of line 4 is the pivot point of the entire paper, and we have fully exposed why it works physically. We are ready to look at the hard data.
Section V results. We are going to translate the visual data from figures 1, 2, and 3 into an audio-friendly analysis.
Good idea.
Figure 1 looks at the 128,120 extended Hamming code.
Right. A Hamming code is one of the oldest, simplest error-correcting codes. It's a perfect baseline test to ensure the math actually functions correctly.
The authors note that the order statistics analytical bound, the covered space probability, and the Monte Carlo hardware simulation all perfectly align on the graph. The lines literally perfectly superimpose on each other.
Which is the absolute validation of the grueling math in Section 3. It proves beyond a shadow of a doubt that their complex analytical formulas perfectly predict the physical reality of the silicon.
They then test sets with Q equals 16 patterns and Q equals 64 patterns. At Q equals 64, they observe a catastrophic failure of the standard chase-to-second algorithm compared to the others. The chase-to-toter with P equals 6 performs drastically worse. Why does the standard widely used chase fail so badly here compared to MCOC?
Well, because at P equals 6, chase-to-second blindly generates all 2 to the 6th, or 64 patterns, in a tiny, dense cluster strictly over the 6 least reliable bits.
So it's all bunched up.
Exactly. It hyperfocuses all its geometric spheres in one tiny localized area of the hypercube. But the physical noise doesn't care about our sorting. It isn't always perfectly confined to the 6 least reliable bits. Sometimes the 7th or 8th bit flips due to a random quantum fluctuation.
Right.
MCOC, utilizing the logistic weight and geometric pruning, spreads its 64 patterns out far more intelligently, casting a wider, more sparse net that catches vastly more realistic error distributions across the entire block.
Which brings us to figure 2 and 3, the heavy hitter results. They are testing the 256,239 extended BCH code. They explicitly state this is the exact component code used in OFEC, the 400 gigabit optical standard powering data centers globally right now. They note that the literature previously established you needed 93 restricted chase patterns to achieve the required error threshold for OFEC. But here is the climax of the paper. They plot the block error rate, And the MCOC algorithm, using only 42 test patterns, completely outperforms the restricted chase algorithm using 93 patterns. Let's analyze the physical implications of this deeply. If you are an optical hardware designer, what does it mean that you can achieve better error correction with less than half the computational attempts?
It is a total paradigm shift.
Mhm.
In a fiber optic transceiver running at 400 or 800 gigabits per second, the BCH decoder is processing billions of bits every single second. Every single test pattern you require means etching another physical bounded distance decoder circuit into the silicon wafer.
Wow.
If you drop the design requirement from 93 patterns down to 42 patterns, you instantly cut the physical surface area, the decoding logic, in half. You cut the electrical power consumption in half. You drastically reduce the thermal heat the chip generates.
And heat is the big issue, right?
Yeah. In high-speed optics, thermal dissipation is the ultimate ceiling. If your chip gets too hot, it melts, or you have to build massive, expensive cooling systems. This algorithm directly pushes back the physical thermal limits of what we can actually engineer.
In Figure 3, they plot the list error rate against the sheer number of patterns Q at a fixed SNR of 5.5 decibels. The graph physically shows that as you increase the number of allowed patterns, the performance gap between MCOC and the chase variants doesn't just stay parallel, it physically grows wider.
Because MCOC scales intelligently based on geometry. As you give standard chase more patterns, it just exhaustively fills in more dense, completely redundant overlapping spheres in a localized area. It's checking the same errors twice.
And MCOC doesn't do that.
Exactly. As you give MCOC more patterns, it geometrically spaces them out further and further into the dark space of the hypercube, capturing high-value probabilities that chase never even approaches.
Completeness check on the results section. Have we ensured all data points, the optical fiber physical implications, and the geometric scaling from the figures are fully addressed?
The visual data has been thoroughly translated and connected directly to the physical thermal realities of silicon design. We are ready to plunge into the conclusion and the deepest layer of the unabridged protocol. The mathematical appendices.
Let's do it. Section 6, Conclusion. The authors summarized that they evaluated 3 accurate methods for estimating the list error rate and proposed an algorithm for finding test pattern sets that performs almost as good as optimal in polynomial time. They include a brief acknowledgement to a Benjamin Castellaz for pointing them to the methods of efficient order statistics calculations. And now we descend into the appendices. We begin with Appendix A, the formal proof of Lemma 1, which we touched on earlier, to prove the induction.
Right. Lemma 1 was the mathematical claim that adding a specific logistic weight pattern rho sub q covers a very strictly defined set of new error vectors.
The proof traces the logic using 3 sets of covered space: script v sub 1, script v sub 2, and script v sub 3. Let's unpack the physical logic of this. They state the total set of error vectors covered by the new pattern is mathcal v and mathcal v in the set script v equals the set of rows sub q o plus 1 sub k, such that k is in the power set of n and the cardinality of k is less than or equal to t. That's the full mathematical definition of the Hamming ball.
Yes, it is. And the proof relies on a process of systematic elimination, subtracting the parts of that ball that were already guaranteed to be covered by earlier patterns due to the sorting rules.
They define script v sub 2 as the vectors within the ball with a Hamming weight smaller than t. They state by property 1 these are mathematically already covered by lighter patterns. They define script v sub 3 as vectors covered by patterns with the exact same weight, but a lower binary representation, which are covered by the deterministic tie-breaking rules of definition 1, leaving only script e sub 1, the exact vectors with exactly tied additional errors in positions greater than Imax.
It's an immaculate logical deduction. They rigorously define the total geometric volume of the sphere, mathematically subtract the volumes mandated by the sorting and tie-breaking rules, and demonstrate that what remains, the exclusive, newly conquered territory of the new pattern, is exactly what Lemma 1 predicted. It seals the induction proof shut.
Which brings us to Appendix B, Order Statistics Setup. This is the absolute mathematical core of the paper, the underlying engine running method A. The unabridged protocol mandate requires maximum verbosity here. Every single equation from 11 through 19 will be executed using the perfect pronunciation protocol, and then we must immediately explain the physical why.
Let us begin the descent.
Equations 11 and 12 define the density functions of the reliability alpha sub I. First, for a correct hard decision, Fargreases frac q sigma x plus 1 and cased otherwise, f sub c of x equals the piecewise function, q sub sigma of x plus 1 divided by q sub sigma of 1 for x greater than or equal to 0 and 0 otherwise. Second, for a wrong hard decision,
Frequencies begin cases frequencies, rag q sigma in text otherwise, and cases f sub e of x equals the piecewise function. Q sub sigma of x minus 1 divided by 1 minus q sub sigma of 1 for x greater than or equal to 0 and 0 otherwise. Frac q sigma if x f sub e of x equals the piecewise function. I need you to explain this physically. Why are the probability distributions for correct and incorrect decisions fundamentally mathematically different?
It comes down to conditional physical reality on the wire. If the hard decision was correct, it means the analog noise wasn't violent enough to push the voltage over the 0 threshold. Because it stayed safely on the correct side, the reliability, the absolute distance from 0, is heavily biased to be a higher number. That is what f sub c of x maps.
Okay, and for the wrong decision?
If the hard decision was wrong, it means the noise was strong enough to push it across the boundary. But it's highly unlikely the noise was so strong that it pushed it deep into the wrong territory. It likely barely crossed the line.
I see.
Therefore, the reliability distribution of a flipped bit, f sub e of x, is fundamentally shifted towards 0. The hardware sees these physical realities as entirely different statistical curves.
That makes perfect physical sense. Next, equations 13 and 14 define the corresponding cumulative distribution functions, the CDFs, by integrating those densities. For correct decisions, FCX, begin cases, frac q sigma 1, x f sub c of x equals the piecewise function, q sub sigma of 1 minus q sub sigma of x plus 1, all divided by q sub sigma of 1 for x greater than or equal to 0 and 0 otherwise. For wrong decisions. Phi1 q sigma 1 q sub 1 x n cases f sub e of x equals the piecewise function, 1 minus q sub sigma of 1 minus q sub sigma of x minus 1, all divided by 1 minus q sub sigma of 1 for x greater than or equal to 0 and 0 otherwise.
This is standard probability theory. The CDF simply tells the math the accumulated probability that a measured reliability voltage falls below a certain specific threshold x.
Now we introduce the sorted order statistics. The B reliabilities where the decision is actually wrong are denoted beta, sorted from 1 to B. The n minus B correct reliabilities are denoted gamma, sorted from 1 to n minus b. Equations 15 and 16 define their probability density functions.
Theta BIA x, FEX I1, 1 F sub I F sub beta B comma I of x equals capital theta of B comma I times F sub E of x times F sub E of x to the power of I minus 1 times 1 minus F sub E of x to the power of B minus x, gamma raised E, equals capital theta of M minus B comma J times F sub C of x times F sub C of x to the power of J minus 1 times 1 minus F sub C of x to the power of N minus B minus J. Explain this construct. Why are we multiplying the density by the CDF raised to specific powers? What is happening physically?
This is the core magic of order statistics. We are asking a highly specific question. What is the physical probability that the ith smallest reliability measurement in a set of sorted bits is exactly value x?
Okay, so how does it calculate that? For that to be true, 3 independent physical conditions must happen simultaneously. First, one single bit's reliability must land exactly on x, that's the f sub e of x term. Second, exactly I minus 1. Other bits must be physically smaller than x, that's the CDF f sub e of x raised to the power of I minus 1.
Right.
Third, the remaining b minus I bits must be physically larger than x, that's the 1 minus CDF term. The theta at the front is the combinatorial multiplier accounting for all the different ways you can route those specific variables into those 3 mathematical buckets.
Equations 17 and 18 extend this framework to joint probability density functions for subsets of these ordered variables, using a massive product series over the intervals between the variables. We will acknowledge the structural complexity here as standard order statistics mechanics from David and Nagaraja, as cited in the paper, because we need to walk through example 1, where they illustrate how these constraints actually work in practice. They propose a toy example. A 7-4 Hamming code with t equals 1 decoded with q equals 19 logistic weight test patterns. I'm going to read all 19 patterns to trace the progression of the logistic weight and the binary tie breaking.
Please do. Pay close attention to how the physical sorting forces the ones to shift to the right, to higher indices, steadily increasing the weight, and how the hardware tie-breaking rules we discussed are rigorously applied.
Here is the ordered set. 0, 0, 0, 0, 0, weight 1, 0, 0, 0, 0, 0, 0, weight 0, 0, 0, 0, 0, 0, weight 3. Notice the tie here, broken by Hamming weight first, then binary representation. 0, 0, 0, 0, 0, 0, 0, 0, 0, Wait 40L0000, wait 401, 0000000, wait 5, 00000, wait 5, 101000000, wait 5, non-euro 0000000000000, wait 6, 1000000, wait 6, 1100000000000, wait 7, 11000000000, wait 7, 100000000, wait 7, 1000000, wait 8, and the 19th pattern of 0, and the 19th pattern of row. They consider the marginal probability of adding this specific 19th pattern. The condition requires evaluated at 4 equals row evaluated at 4. This translates to constraints on the ordered reliabilities. The pattern has 1s at positions 1, 2, and 4. This mathematically forces those specific sorted variables to correspond to physical errors. The 0s at positions 3, 5, 6, and 7 correspond to correct bits.
Yes. They set up the inequality chain based on the physical sorting of the bits by the hardware. Since the receiver physically sorted the bits by voltage reliability, position 1 must be less reliable than position 2, which must be less than position 3, and so on.
They write the constraint chain exactly. Beta 5, 1 is less than or equal to beta 5, 2, which is less than or equal to gamma 2, 1, which is less than or equal to beta 5, 3, which is less than or equal to gamma 2, 2. They define the set of non-trivial conditions F, isolating only the constraints that aren't automatically fulfilled by the fundamental definition of order statistics. Which brings us to the grand finale of the math protocol, equation 19. The multidimensional integral that actually calculates this exact constraint probability. The equation is written as the integral over the space r to the power of the cardinality of f greater than or equal to 0 and constrained by f of the joint density f sub beta b comma I sub f of x sub I sub f times the joint density f sub gamma n minus b comma j sub f of y sub j sub f dx sub I sub f sub j sub f. The equation is written as. Okay, listening to that syntax is honestly like staring into the matrix.
In an audio format, that just sounds like an impenetrable wall of Greek. Let's pull that apart. Physically, what is this integral actually calculating for the hardware?
Fair point. Visually, this is a calculus nightmare. You are attempting to mathematically integrate over a multidimensional space where the physical boundaries of the space itself are warped and constrained by those F inequalities we just defined.
Right.
Doing this analytically with pure calculus for anything beyond a tiny 7-bit toy example is functionally impossible. The equations become so massive they break standard mathematical software.
Which perfectly explains their final pivot in the last paragraph. Efficient Monte Carlo integration for order statistics. They openly state that solving the multidimensional integrals numerically is prohibitively complex, so they use Monte Carlo integration via the inverse CDF method. They sample from the joint distributions and simply count the ratio of tries where the conditions F are fulfilled.
It's a computationally brilliant escape hatch. You use the rigorous, brutal, analytical framework of order statistics to precisely define the boundary of the multidimensional volume you need to measure. But then, instead of trying to integrate that massive volume with pure calculus, you essentially throw millions of random darts at the space using inverse CDF sampling, and you simply count how many darts land inside the boundary constraints. It gives you the exact answer of equation 19 in a fraction of the time without crashing your simulation.
Final completeness check. We have executed the perfect pronunciation protocol through the entirety of Appendix B, traced the physical logic of the toy example, demystified the multidimensional integral, and justified the Monte Carlo integration escape hatch. Are we clear?
We have left absolutely no stone unturned. The unabridged protocol is totally fulfilled. The mathematical foundation has been entirely exposed.
Then let us zoom out. If you've tracked with us through this, we have gone on an epic journey. We started by contextualizing the origins of high-rate BCH codes in modern optical standards. We traversed the physical geometry of Hamming balls in n-dimensional hypercubes. We analyzed the NP-hard limitations of greedy algorithms and submodular functions. And we just climbed out of a multidimensional Monte Carlo integral mapping the probabilistic space of sorted random variables.
It's a lot of math.
It is. And all of this staggering, dense mathematical architecture serves one highly practical purpose: to design a better test pattern algorithm, MCOC, that pushes data through a noisy fiber optic cable 0.2 decibels more efficiently.
Because, as we established at the beginning, that fraction of a decibel is the difference between expanding the global internet efficiently or hitting a physical thermal wall in our silicon design.
Which leaves me with a profound, lingering thought for you to take away.
If you design hardware, this MCOC algorithm should make you sit up in your chair, because dropping from 93 test patterns to 42 means you just cut your chip's thermal output in half. The authors proved we can intelligently predict and map the covered space of errors with far greater efficiency than brute force. They prove that throwing out redundant, overlapping geometries, that explicitly skipping the things you already essentially know based on physical distance, is the absolute key to massive performance gains. If we apply this MCOC algorithm, this fundamental philosophy of maximizing coverage based on predictive reliability, rather than demanding absolute overlapping certainty, what other areas of computer science or even human decision-making could be optimized?
That's a great question.
Where else in our designs are we wasting immense energy demanding 93 brute force patterns of certainty when 42 intelligently spaced, probabilistically mapped patterns would actually yield a cleaner, faster result? Because if the physical limits of optical fiber and silicon heat dissipation are fixed, mathematical algorithms like this are the only way we push the boundaries of data transmission deeper into space or further into the quantum realm.
It is a philosophy of elegant efficiency in the face of inevitable universal noise.
Thank you for staying with us through the unabridged protocol. The diagnostic waters of the digital world might be murky and probabilistic, but as we've seen today, the underlying mathematics fighting to keep it clear are beautiful, precise, and relentless. Keep diving deep.
You know, usually when we talk about sending a message, whether it's like a text message or an email or even streaming a 4K movie to your TV, there's this underlying expectation of just, well, pristine delivery.
Right, yeah. It feels like handing someone a sealed envelope.
Exactly. You write the message, put it in the mail, and it arrives looking exactly the way it did when it left your hands.
And, I mean, it is totally designed to feel that way. The entire user interface of the modern digital world is built to make communication feel like a solid, just binary reality.
It either sent or it didn't.
Exactly. It's clean, it's instant, and, well, it's perfect.
And that is incredibly comforting. You know, we desperately want our digital lives to feel robust. But the reality of what is actually happening underneath all that software is anything but clean.
Oh, it's a mess.
Right. Once you step out of the software and into the world of physical telecommunications.
The copper wires and fiber optics.
Yeah, the literal cables crossing the Atlantic Ocean or the radio waves bouncing around in the atmosphere, that pristine envelope is suddenly being driven through like a Category 5 hurricane. We're looking at a physical transmission landscape that is incredibly violent.
It really is the absolute definition of a chaotic environment. You're taking perfect logical ones and zeros, and you are turning them into physical pulses of light or electricity. And then you just blast them thousands of miles through mediums that constantly degrade and distort them.
Right.
By the time they reach the other side, they don't look like ones and zeros at all. They look like a messy, blurry statistical nightmare.
And figuring out how to read that blur, like how to salvage the original message from that hurricane of noise, is exactly where we are heading today. So welcome to this deep dive.
It's going to be a good one.
Yeah, and if you are listening to this, you are really in for something unique. Today, we are initiating what we call the unabridged protocol.
The unabridged protocol, which is a very specific, intense way we are going to approach today's material.
Right. So what does this actually mean for you, our listener? It means we are going to deliberately slow down time. We are operating under the assumption that we have basically infinite time to get this right.
We are rushing.
Exactly. Instead of just skimming a source for a few, fun cocktail party facts, we are going to deconstruct our single source material today strictly linearly. We are looking under every single mathematical rock.
And we're going to explain the why behind every complex concept rather than just throwing jargon at you and moving on.
Because rushing through math just creates confusion. But if we slow down, if we explore the physical realities behind these formulas, we build a true foundational understanding. So our source material today is a highly technical telecommunications paper.
It's titled Chase-like Decoding, Test Pattern Design and Performance Analysis.
Right, and it's written by Tim Janz, Simon Obermüller, Andreas Zunker, and Stephan Brink from the University of Stuttgart.
It's really a phenomenal piece of work. It gets right to the heart of error correction. Like, how do we build systems that are smart enough to guess what the data should have been,
even when the physics of the channel have completely mangled it.
Now, because we are strictly following this unabridged protocol, we have a rule. We are not going to jump from topic to topic without making sure the foundation is absolutely solid. So periodically, we are going to pause and do a completeness check.
Right, a self-correction mechanism to make sure we haven't left any nuances behind.
Exactly. We'll explicitly ask if we missed anything, confirm it, and state that we are moving to the next line. It keeps us honest.
And it keeps the narrative totally grounded for you listening.
Okay, so let's unpack this. We start at the very beginning, right, with the title and the abstract. Let's look at that title again. Chase-like decoding, test pattern design and performance analysis. What exactly does chase-like imply here?
So that is a direct historical nod to David Chase. Back in 1972, Chase published this truly seminal paper on algorithms for decoding block codes.
And he used channel measurement information, right?
Exactly, because before Chase, error correction was mostly a hard binary affair. A receiver would look at a messy signal and just force a decision. It would say, okay, I think that's a 1, or I think that's a 0.
No room for doubt.
Right, and once it made that hard decision, it threw away all the nuance. But Chase came along and said, wait, what if we use the reliability information from the channel itself?
Like how confident the channel actually is.
Yeah. If the receiver is only, say, 51% sure something is a 1, we should treat that specific bit very differently than a bit the receiver is 99% sure is a 1.
So when the authors of our paper say chase-like, right in the title, they are immediately telling the academic community, hey, we are standing on the shoulders of that 1972 breakthrough. We are using that soft reliability information to generate a list of possible correct answers.
They are entirely in the business of probabilistic guessing.
Okay, so then we get to the abstract. The authors state their premise super clearly. They mention that they are evaluating test pattern sets using 3 distinct methods: order statistics, covered space, and Monte Carlo simulations.
Right.
And then they drop the hook. The whole reason this paper exists, they state they propose a new algorithm that yields up to a 0.2 dB improvement for high-rate BCH codes.
That 0.2 dB is the core thesis.
So let's ground this for you listening. Before we get into what a 0.2 decibel gain actually means, what exactly is a test pattern in this context?
Well, it's essentially a structured set of hypotheses.
Think of it like a detective investigating a crime scene. So the detective arrives at the scene, and that represents our receiver getting the corrupted data. There are witnesses there, but they are super unreliable. The channel noise has distorted their memories.
Right. The witnesses are the individual bits.
Exactly. So the detective has to test different hypotheses. Like, what if the first witness is lying? Let's run that scenario. Okay, what if the second witness was mistaken, but the first was telling the truth?
That's a great analogy.
A test pattern is simply a structured set of those what-ifs. We purposefully flip certain bits that we suspect might be wrong based on how unreliable the channel said they were, and then we run our decoder to see if the resulting string of data makes logical sense.
Right. Does it fit the rules of the code? A test pattern is a targeted hypothetical.
So we have these test patterns, and the authors are claiming a 0.2 dB improvement in how we use them. Now, I really want to emphasize why this matters, because to a layman, 0.2 decibels sounds incredibly small.
Oh, it sounds like a rounding error.
Right. But in physical telecommunications, especially in high-rate data center interconnects or those massive long-haul optical cables running across the ocean floor, you are transmitting trillions of bits per second.
The scale is just unfathomable. So a 0.2 dB coding gain is actually massive. It means you can either transmit that exact same ocean of data using less physical power, or
push it further.
Exactly. You can push the data over a much longer physical distance before the signal degrades so much you lose it. Or you can pack even more data into the exact same frequency band.
So when you are laying cable across the Atlantic, a 0.2 dB gain might literally mean you don't have to build and sync an entirely new multi-million-dollar repeater amplifier station right in the middle of the ocean.
At scale, 0.2 DAB represents massive efficiency and financial gains in actual infrastructure. Upgrading silicon or laying more physical cable is wildly expensive. But upgrading the algorithmic logic inside the receiver, that is practically free by comparison.
It is the math doing the heavy lifting, so the hardware doesn't have to. Okay, so that covers the title, the authors, and the abstract. Time for our first mandatory completeness check. Have we missed any nuances in this opening section?
I think we have thoroughly unpacked the abstract. We know the destination, which is that 0.2 dB gain, and we know the heritage of the Chase algorithm. Let's proceed to the introduction.
Excellent. Moving to section 1, the introduction. We are taking this paragraph by paragraph. Paragraph 1 introduces BCH codes. The authors write that binary Bose-Ray Chaudhuri Hocquenghem codes, or BCH codes, are widely used due to their good minimum distance and efficient decodability.
That's a mouthful, but the history is fascinating. BCH codes were invented way back around 1959 and 1960. They're a class of cyclic error-correcting codes.
And they are universally adopted, right?
They are. And what makes them so popular is their mathematical rigidity. When you design a BCH code, you can mathematically guarantee that it will correct a very specific, predetermined number of errors. If you absolutely need a code that corrects exactly 4 errors out of every 100 bits, you build a BCH code to do exactly that.
The paragraph also mentions they are often used in concatenated coding schemes, specifically pointing to data center interconnects and long-haul optical communication like OEPC. Why concatenated? Why don't modern systems just use one massive, perfect code?
Oh, it's all about computational efficiency. Think of concatenation like a set of nested water filters. The transmission channel is incredibly messy, so you have an inner code that acts like a coarse sieve.
It catches the big stuff.
All right, it runs incredibly fast and catches the vast majority of the random errors introduced by the hurricane of noise. But some tiny impurities, some rare errors, will inevitably slip through that coarse sieve.
Do you need a backup?
Exactly. You have an outer code, like the KP4 Reed-Thalman code the authors mention, acting as a fine mesh filter to catch whatever the inner code missed. BCH codes are fantastic as component codes in these massive architectures because they are incredibly fast to decode in hardware.
Okay, that covers the first paragraph. Completeness check. Are we clear on what a BCH code is and why it's used in concatenated schemes?
We are clear. Let's move to paragraph 2.
Paragraph 2 highlights the problem. The authors point out a major limitation. They state that the performance of hard decision decoding with bounded distance decoders has a large gap to the theoretical maximum likelihood performance.
This is the absolute crux of the problem. We need to clearly establish the difference between hard and soft decisions right now, as it is the bedrock of everything that follows.
Let's slow the pace down for you listening. Imagine I am looking at a really blurry, degraded photograph of a coin on a table, and I have to tell you if it's heads or tails. A hard decision is strictly black or white. I look at the blur, I force a choice, and I just say it's heads. Or in telecom, it's a 1. I don't give you any context about my doubt.
Right. And bounded distance decoders, those incredibly fast hardware decoders we just talked about, historically they only accepted hard decisions. They only wanted to be fed absolute 1s and 0s.
But a soft decision introduces shades of gray. A soft decision is me looking at that same blurry photo and saying, look, I am 85% sure that is heads, but given the blurriness, there's a 15% chance it's tails. I am passing along the actual probability.
Exactly. And the problem with legacy systems is that when you force a hard decision early at the receiver, you literally throw away all that valuable probability information. You treat a bit you were 51% sure about identically to a bit you were 99% sure about.
Which seems incredibly wasteful.
It is. The performance gap the authors mention between hard decision decoding and maximum likelihood performance is the efficiency you lose by throwing away those shades of gray. To close that gap, we need decoders that can take soft inputs.
Completeness check for paragraph 2. Have we clearly defined the gap between hard decisions and the ideal maximum likelihood?
I believe we've thoroughly unpacked it. We understand why throwing away probabilities is bad. Let's proceed to paragraph 3.
Paragraph 3 brings us back to Chase 2. The authors explain that the Chase 2 algorithm bridges this gap by generating 2 to the power of p-test words. They also briefly mention other modern soft input algorithms like GRAND, which stands for Guessing Random Additive Noise Decoding, and they bring up logistic weights for the first time.
Chase 2 is the workhorse here. It looks at the soft information, identifies the soonest reliable positions, and just generates a massive list of candidates by testing combinations of those specific bits.
And GRAND is sort of a cousin to this idea, right?
Yeah, GRAND is another way of guessing noise patterns. But the paper mentions it mostly to situate their own work in the modern context of logistic weights.
Okay, completeness check for paragraph 3. Are we good on Chase II generating 2 to the power of p combinations?
Yes. The historical context is set. Moving to paragraphs 4 and 5.
Paragraphs 4 and 5 state the gap in the literature. They note that while Chase-like algorithms are known, there is a lack of literature analyzing test patterns specifically for high-rate BCH codes. So they introduced their 3 LER, or list error rate, evaluation methods, and their new pattern design.
And just to clarify for the listener, high rate means that almost all the bits you are sending are actual useful data. Very few bits are used for redundancy or error correction.
It's a highly efficient code, but it leaves very little margin for error.
Exactly. The authors are setting the stage to prove that for these specific demanding codes, they have found a demonstrably better way to guess the errors.
Final completeness check for the introduction section. Have we missed any setup logic before we hit the hard math?
The introduction is fully unpacked. We know the problem, we know the codes, and we know the goal. We can move to Section 2.
Moving to Section 2, Preliminaries and the Channel Model. Section 2A. This is where the paper defines its language. They start with basic set notation. They define the power set notation P sub k, representing all possible combinations of bit flip.
But it's just formalizing how we group the errors.
They also define element-wise addition over F sub 2, and then we hit the distance metrics. They define the Hamming weight of a vector, denoted as W sub h of u, and the Hamming distance, D sub h of u, comma v.
So the Hamming weight is simply counting the number of non-zero elements in a vector. If you have a vector of errors and it looks like 1, 0, 1, 1, the Hamming weight is simply 3, because there are 3 errors.
Just a straight count.
Right. And the Hamming distance between two vectors is just the number of positions where they differ from each other.
And this leads to a really crucial visual concept for this paper, the Hamming ball. They define the Hamming ball of radius r centered at a specific vector u.
We really need to visualize this one. Imagine you are standing in a massive, completely empty room. And you, your physical body, represents a valid, perfect code word.
Okay, I'm the code word.
Now, reach your arms straight out. The length of your arms represents the radius, which in this case is the error correction capability of the bounded distance decoder. Let's call that radius t.
So T is my arm span.
Exactly. Anything you can physically touch within that sphere, within that Hamming ball, gets automatically corrected back to you. If the channel noise corrupts the signal, but it lands somewhere inside your reach, the decoder successfully pulls it back to the center. You successfully decode the message.
But if the hurricane of noise pushes the signal outside of my arm span,
Then the bounded distance decoder fails. It can't reach it. The signal is just lost in the dark.
that is a brilliant visual. Keep that Hamming ball in mind because it is going to be vital when we get to the covered space. But right after defining the Hamming weight, the authors introduce a massive conceptual shift. They define the logistic weight.
This is where the paper starts getting really, really clever.
So the logistic weight, W sub L of u, is defined as the sum from I equals 1 to n of I times u sub I.
Because Hamming weight just blindly counts the errors. It treats every single error equally. But logistic weight multiplies the value of the bit, which is 1 if we flip it and 0 if we don't, by its index position, denoted by I.
And crucially, we are assuming all the bits have already been sorted by reliability.
Right, so position 1 is the absolute least reliable bit. Position n is the absolute most reliable bit.
I have an analogy for this. Think of this like packing a grocery bag at the store. The items you bought represent the bits in our data stream. The really fragile items, like the bread and the eggs, represent our least reliable bits. The channel has battered them. We aren't sure about them at all.
So you put them at the top of the bag.
Exactly, at the top. And the heavy, indestructible cans of soup are our most reliable bits. We are very confident in them. You put them at the absolute bottom of the bag.
Okay, I follow.
The index represents how deep in the bag an item is. Now, if we use the old method, the Hamming weight, it just counts how many items you squashed on the way home. I squashed 3 items. It doesn't care what they were.
It could be 3 eggs or 3 cans of soup. It just says 3.
Right. But logistic weight is a weighted penalty system. It penalizes you based on where in the bag the squashed items were. Squashing the eggs at the very top of the bag at index 1 carries a very small penalty. We expected them to break. They were unreliable.
Yeah, that makes sense.
But if you tell me you somehow managed to squash the solid steel can of soup at the very bottom of the bag, at index N, the logistic weight applies a massive heavy penalty. Because mathematically, flipping a bit that the receiver was 99.9% confident about should be an incredibly rare event.
That actually tracks perfectly. If I'm holding that grocery bag, the logistic weight beautifully captures the entire probability distribution of the channel in a single, simple integer value. It is a way of scoring how likely a specific pattern of errors is, based not just on how many errors there are, but exactly where they occurred relative to our confidence.
Completeness check on these definitions.
Yeah.
Have we fully established Hamming weight versus logistic weight?
We have. The grocery bag analogy nails it. Let's look at the physical channel model now.
Okay, still in section 2A, the channel model. The authors state they are considering transmission over a binary input additive white Gaussian noise channel, an AWGN channel, and they are using BPSK modulation, which is binary phase shift keying.
Let's break down the physical reality of that. The paper states that the binary input of 0 maps to a physical +1, and a binary 1 maps to a physical -1.
Because when we send data over a wire or a fiber optic cable, we don't literally send the abstract numbers 1 and 0. We send physical energy.
Exactly. In BPSK, we might say a positive voltage, let's say +5 volts, represents a logical 0, and a negative voltage, -5 volts, represents a logical 1. So our transmitter is just rapidly alternating between positive and negative voltages.
But then the AWGN channel attacks it. Additive white Gaussian noise. Let's break those words down.
Sure. Additive means the noise is literally just added to our physical voltage. White means it contains all frequencies, sort of like white light. And Gaussian means the noise follows a standard bell curve distribution.
So physically, what is this noise?
It represents the random thermal jiggling of electrons in the receiver circuitry, or ambient radiation. So you send a perfect +5 volts, but the thermal noise adds a random -2 volts to it. So the receiver actually measures +3 volts.
But it's still positive, so the receiver correctly guesses it was a logical 0.
Right. But what if the noise is incredibly strong? What if the noise is -6 volts? You send +5, the noise adds -6, and the receiver measures -1 volt.
Oh, wow. The noise has physically pushed the signal across the 0 threshold.
Exactly. The receiver looks at the negative voltage and incorrectly guesses it was a logical one. That is exactly how a physical bit flip occurs in the real world.
And the authors mathematically capture this. They introduce the first major formulas here. They define the probability of exactly B bit flips occurring. So executing the mass pronunciation protocol here. The probability of B bit flips is given by equation 1. It is written as PEB, binom minum B 1Q1 sigma, PQ1 sigma NB ep. For you listening, we read this phonetically as P of E sub B equals N choose B times 1 minus Q of 1 over sigma, all to the power of B times Q of 1 over sigma to the power of N minus B.
Perfect. Rather than getting lost in the algebra of the Q function, let's look at the mechanism. The Q function is calculating the exact area under the tail of the bell curve of the noise that pushes past our voltage threshold. It gives us the raw probability that the noise was strong enough to flip a single bit.
And then equation 1 scales that up.
Yeah, the binomial coefficient scales it up to figure out the probability of getting exactly B of those flips across the entire message block of N bits.
And immediately following that, in equation 2, they define the baseline performance. They calculate the probability that the bounded distance decoder actually succeeds, executing the protocol again. The probability for bounded distance decoding is written as PBDDD equals a sum I, which we read as P sub BDD equals the sum from I equals 0 to T of P of E sub I.
And this flows logically right from the Hamming ball concept we discussed. If the decoder can correct up to T errors, what is the probability it works? It's simply the probability of the channel creating exactly 0 errors plus the probability of 1 error plus 2 errors all the way up to exactly T errors.
Because if the channel creates ent plus 1 error,
you are outside the Hamming ball and the decoder fails. So equation 2 is the exact mathematical baseline. It is the number the rest of the paper is trying to beat.
They also explicitly define the channel reliability values here. They say the channel output Y is sorted by reliability, where the absolute value of L equals 2 over sigma squared times the absolute value of Y. Why do we care so much about the least reliable bits?
Because that's where the errors live. If you're looking for a needle in a haystack, you don't search the parts of the haystack you already cleared. The least reliable bits, the ones closest to the 0 voltage threshold, are statistically where the vast majority of all channel errors occur. Sorting them is how we focus the algorithm's attention.
Completeness check on section 2A. We have covered the BIAWGN channel, BPSK modulation, equation 1 for bit flip probability, and equation 2 for the BDD success baseline. Have we missed any underlying mechanics here?
I think the foundation is rock solid. We understand the physical problem and the mathematical baseline.
Let's move to section 2B and IC to see how Chase actually works.
Section 2B, Chase-like decoding. The authors walk through the list generation process. We get our hard decision vector, y hat, from the receiver. We then generate a set of test patterns, denoted as script R. We XOR these patterns with our received data, creating a whole list of test words.
Right.
Each test word is then decoded with a bounded distance decoder, creating a list of candidate code words. Finally, we pick the most likely one from the list. Notice the architecture here. It is essentially running multiple bounded distance decoders in parallel, or sequentially very, very fast. We aren't fundamentally changing the hardware decoder itself. We are feeding it slightly altered versions of the received data.
We apply our test patterns to flip the bits we are suspicious of.
Exactly, and we see if the decoder suddenly clicks and finds a valid code word.
The paper then outlines the variance. Standard Chase 2 tests all possible combinations in the least reliable positions. But then they introduce restricted chase patterns. This set only contains patterns that flip at most a maximum number of bits, Wmax H, in those P positions. Why do we need to restrict it?
The authors explain this beautifully. Let's say we identify the 10 least reliable bits. Standard Chaser 2 would test every single combination, including the scenario where all 10 bits are wrong simultaneously.
Which sounds thorough.
It is, but statistically, the probability of 10 bits failing at the exact same time is infinitesimally small. It's a massive waste of computational resources to actually test that pattern.
Oh, I see.
Instead, it's statistically much smarter to look slightly further down the reliability list, maybe looking at position 11 or 12, and test if maybe just 1 or 2 bits flip there. So you expand your search window to a larger number of bits, but you restrict the total number of simultaneous flips you allow. It keeps the number of tests manageable while covering much more probable error scenarios.
Which leads perfectly into definition 1, logistic weight patterns. They formally state that for a pattern set of size Q, the Q patterns with the smallest logistic weight are chosen. If there is a tie, they pick the one with the smaller Hamming weight, and if there's still a tie, the one with the smaller binary representation.
This formalizes our grocery bag analogy. To build the absolute smartest set of test patterns, we calculate the logistic penalty for every possible error pattern. We sort them from lowest penalty, which means most likely to occur, to highest penalty, which means least likely. And we just lop off the top Q patterns.
And the tiebreakers.
The tiebreakers just ensure the algorithm is mathematically rigorous and completely predictable.
Okay, and what is the ultimate goal of picking these specific patterns? Their authors define it in section 2C, breaking down the error probability. They isolate the crucial metric for the entire paper. The list error rate, or LER, they denote it as P subscript R of C, not in script L.
Right. The LER is simply the probability that the true original code word simply wasn't found by any of our test patterns. We generated our list of candidates, we flipped all the bits we thought were suspicious, but the real answer still wasn't on the final list.
We missed it.
Exactly. If we can minimize the LER, we minimize the overall error of the entire communication system.
So the entire game here is, how do we pick a small set of test patterns that minimizes the chance of the true code word slipping through the cracks?
That is the whole game.
Completeness check for section 2 IB and IC. We've unpacked chase 2, list generation, restricted chase, definition 1 for logistic weight patterns, and the LER. Are we leaving any mathematical stones unturned here?
The LER decomposition is clear. We are ready for the geometric heart of the paper. Let's move to section 2D.
Section 2D, covered space probability calculation. The authors define equation 3, the probability of a vector V given the channel output Y, and then they define the covered space, represented by a script V in equation 4, and its probability in equation 5. Let's execute the protocol for the covered space. The covered space equation is written as math-cowly, vocalized as the covered space script V equals the union over all patterns row in script R of the Hamming ball B subtie centered at row.
So if we connect this back to our earlier visual, imagine the entire universe of possible data vectors is a massive pitch black room.
Okay, I'm back in the room.
The true perfect code word is hiding somewhere in that dark room. Your initial hard decision from the receiver gives you a starting coordinate in the dark. Every single test pattern you generate is you taking a step to a new coordinate in the room.
Okay.
And remember the bounded distance decoder's radius, dt. That radius is a flashlight you turn on at every single coordinate you visit.
I love this. So the covered space, that scripty we just defined, is literally the total volume of the dark room that is illuminated by all your flashlights combined.
Exactly, is the union of all the Hamming balls. And the probability of the covered space, equation 5, is simply the sum of the probabilities of all the individual vectors sitting inside that illuminated area. If the true code word is sitting in the dark, outside the illuminated covered space.
You suffer a list error. You missed it.
You suffer a list error.
So the strategic goal of designing a test pattern set is to essentially arrange your flashlights to illuminate the specific areas of the room where the code word is statistically most likely to be hiding, while overlapping the light beams as little as possible so you maximize your total illuminated volume.
That is the perfect architectural translation of this math. You want maximum coverage of the high probability areas with minimal overlap.
Completeness check on section 2D and equation 5. Do we fully grasp the covered space in the flashlight analogy?
I think the visual of the covered space is exactly what we need to tackle the heavy math coming up. The concept is secure. Let's move to section 3.
Section 3 is performance evaluation methods. The authors want to absolutely prove their pattern designs are superior, and they do it using 3 distinct mathematical methods. Section 3A is the list error rate using order statistics.
Order statistics, right?
They want to quantify the marginal utility of adding a single test pattern to an existing set. If I give you one more flashlight, how much new probability space do you actually illuminate? They define this in equation 6 as the added probability.
Is just the probability that the code word is in the list with the new pattern minus the probability it was in the list without it. Simple enough conceptually.
But then they apply this to the chase algorithm using order statistics, and the formulas become massive summations. Equation 7 is the LER for standard chase 2, and equation 8 is for restricted chase. Let's talk about order statistics. Why is it so complicated?
To understand the mechanism of order statistics without drowning in the algebra, let's use an analogy. If you roll a standard 6-sided die, the outcome is uniformly distributed. Any number has a 1 in 6 chance.
Right.
But what if you roll 5 dice, and I ask you for the probability distribution of only the highest die? That distribution is no longer uniform. It is heavily skewed towards 5 and 6. That is an order statistic.
Because we explicitly sorted our bits by reliability earlier.
Exactly. Because we sorted them from least reliable to most reliable, we can't use standard independent probabilities anymore. The probability that the bit at index position 5 is an error is strictly conditioned on the mathematical fact that its reliability must be greater than the bit at position 4 and less than the bit at position 6.
So the math becomes incredibly complex because every single variable is tethered to the variables around it.
Yes.
Equations 7 and 8 are these giant summations adding up the conditional probabilities of these error vectors, factoring in the error correction capability and the constraints of the test patterns.
Right. And the reason order statistics are so powerful, despite all that complexity, is that they provide an exact analytical calculation. No physical simulations required. If you can clearly define the boundaries of your test patterns, you can integrate over the probability density functions and get the exact list error rate.
But you need those clear boundaries, which is why they introduced Property 1 and Lemma 1. Property 1 states that for a fixed pattern in the logistic weight set, all patterns with a subset of its non-zero positions are also guaranteed to be in the set.
They're establishing a nested structure here. If a complex pattern with 3 bit flips is in your set, the simpler patterns that only flip 1 or 2 of those exact same bits are mathematically guaranteed to already be in your set because their logistic weights are strictly lower.
And Lemma 1 builds on this nested structure to prove that a new logistic weight pattern covers a very specific, cleanly defined new area of the space, which culminates in Proposition 1 and Equation 9. This is a massive summation over the maximum Hamming weight that proves you can perfectly calculate the LER for logistic weights using order statistics.
Equation 9 is the mathematical crown jewel of this analytical section. It proves the math holds up perfectly.
Completeness check on Section 3A up to Equation 9. Have we adequately explained order statistics and Lemma 1?
We have. The die analogy explains the conditional dependencies perfectly. Let's look at the other 2 methods.
Okay, Section 3B is the covered space method, which uses equation 10 to estimate probability using the law of large numbers. And Section 3C is direct Monte Carlo simulation, which is basically simulating the entire transmission system from end to end. Now, I have to push back here for the listener. If order statistics gives us the exact analytically perfect answer in equation 9, why are we bothering with covered space estimations and brute force Monte Carlo simulations? Why do we need 3 methods if they all calculate the exact same list error rate?
It's a really great question, and it comes down to computational utility versus flexibility. Order statistics, the first method, is perfectly exact, but is incredibly fragile. It requires your test patterns to have a rigid, mathematically definable structure, like Lemma 1 just proved for logistic weights.
Right, it needs organized flashlights.
Precisely. If you give the order statistics engine a random, chaotic set of test patterns, the math completely falls apart because the integration boundaries become impossible to define.
So what about covered space?
The second method, covered space, is great for arbitrary chaotic patterns because it doesn't care about structure. It just calculates the geometric volume of the overlapping flashlights. But calculating the exact overlaps of spheres in high-dimensional space is computationally exhausting.
And the third method, direct Monte Carlo.
Direct Monte Carlo is the universal brute force. You just build a virtual channel in software, run a billion simulated packets through it, and count how many fail. It works for literally any algorithm, no matter how weird or unstructured. But it has a fatal flaw. At high signal-to-noise ratios, where errors are extremely rare, say 1 error in 100 million bits, you have to run billions upon billions of simulations just to get a statistically significant result. It takes forever.
I see. So by presenting all three methods, the authors are doing two things. They are providing the tools to evaluate any kind of pattern set, and they are proving that their analytical formulaic math matches the brute force physical reality perfectly.
Exactly. It's a triple verification.
Completeness check on the entirety of Section 3. Are we clear on the three evaluation methods and why we need them?
We are clear. We have our measuring sticks. Now it's time to see what they actually built. Let's move to Section 4.
Moving to Section 4, pattern designs for chase-like decoding. The authors state up front that finding the absolute optimal test pattern set, like the perfect arrangement of flashlights that maximizes coverage with zero wasted overlap, is an NP-hard problem. It's a problem of maximizing submodular set functions.
Right. And NP-hard means that if you want to find the perfect 40 patterns out of trillions of possibilities, testing every single combination to find the optimal arrangement would basically take modern computers until the heat death of the universe. It is physically impossible to solve perfectly. So we have to turn to heuristics. We have to approximate.
They discuss the greedy pattern design. The greedy algorithm iteratively adds the pattern that improves the covered probability the most. It calculates the added space for everything, picks the best one, adds it to the set, and repeats. Yeah. But the authors note that even this greedy approach is too computationally expensive for long codes, because calculating the geometric overlap of the Hamming balls at every step takes way too much time. Wait, hold on. If finding the optimal pattern is NP-hard, and the greedy approximation requires calculating massive multidimensional overlaps, aren't we just trading one computationally impossible task for another? How is this actually faster for a router?
You've hit the exact bottleneck that has plagued this entire field.
Yeah.
And that is exactly why the authors introduced their major breakthrough in Section IVC. They propose a heuristic design rule called Maximally Covered Ordered Candidate Patterns, or MCOC. This is their solution to the computational nightmare.
Okay, let's walk through the logic of this MCOC algorithm. Algorithm 1 in the paper. They provide the pseudocode. They initialize an empty set of patterns. They start a loop that runs until they have the desired number of patterns, Q. Inside the loop, they fetch the most likely error pattern based on probability. And then we hit line 4. Line 4 checks the minimum Hamming distance between this new candidate pattern and every single pattern already sitting in our selected set.
If that minimum distance is strictly greater than our radius t.
This is the genius of the entire algorithm right here. Line 4 is the magic trick. Remember the flashlights. To know if a new flashlight is illuminating new space, the greedy algorithm tries to calculate the exact volume of light. That takes forever.
Right.
MCOC says forget the volume. It just looks at the center points of the flashlights and calculates the simple Hamming distance between where you are standing and where the new flashlight is. If that distance is greater than the radius of the beams, TT, it mathematically guarantees that the spheres do not completely overlap.
Because the center points are physically far enough apart? Exactly. It is a rapid, computationally cheap proxy for calculating the covered space. Instead of doing intense volume integration, it just measures a straight line. If the centers are further apart than the radius, it means the new flashlight beam is guaranteed to illuminate at least some new uncharted area of the dark room.
That is absolutely brilliant. It uses probability to pick the general area and simple distance to ensure efficiency. This efficiency right here, checking the linear distance instead of calculating the volume, is exactly how a data center router processes a terabit of your Netflix streams a second without melting the silicon. It avoids the heavy math.
It's an incredibly smart, lightweight way to approximate the heavily complex, greedy algorithm.
So, synthesizing the algorithm, instead of doing the impossible math of perfect optimization or the heavy math of greedy volume calculation, MCOC just picks the most probable errors and makes sure they are physically spaced far enough apart so they don't waste overlapping effort. Completeness check for algorithm 1 in section 4. Are we missing any nuances on how the MCOC algorithm functions before we look at the actual data?
I think we've unpacked the exact mechanism that makes it special. The proxy of distance for volume is the absolute key takeaway. Let's see if it actually works. Let's move to the results section.
Moving to section V, results, the payoff. They start with figure 1, analyzing a relatively small 128,120 extended Hamming code. They plot the list error rate using all three methods: direct Monte Carlo, order statistics, and covered space for 128 logistic weight patterns.
And if you look at the graph in the paper, the lines for all three methods sit exactly on top of each other. They perfectly align. This is the visual proof that their complex order statistics math from Section 3 is perfectly accurate. The analytical theory perfectly matches the brute force simulation.
They then evaluate performance for sets of 16 patterns and 64 patterns. For 16 patterns, standard chase performs slightly worse than logistic weights in MCOC. But for 64 patterns, standard chase the second falls off a cliff compared to the others. Its error rate remains stubbornly high while the MCOC algorithm plunges towards zero. Why?
Which empirically proves our earlier point. Standard chase the second is incredibly inefficient. It wastes its limited tests on highly improbable combinations, like all 6 of the fragile eggs breaking simultaneously, while completely ignoring much more probable single errors further down the reliability chain.
It's searching the wrong part of the room.
Exactly. MCOC and logistic weights dynamically prioritize the scenarios that actually happen in the real world.
But the real-world impact is truly highlighted in figures 2 and 3. They analyze the 256,239 extended BCH code. This isn't just an academic example. The authors explicitly note this code is used in the OFEC standard open forward error correction for 400 gigabit optical networking.
This is the literal backbone of the internet.
Right. They show that to achieve a specific target performance threshold, the standard restricted chase algorithm requires testing 93 different patterns.
But the MCOC patterns, the algorithm we just walked through, the one that measures the distance between the flashlights, it achieves the exact same or even better performance using only 42 patterns.
Wow. We just proved that by smartly picking which 42 patterns to test using this MCOC logic, we beat an algorithm that is working more than twice as hard, testing 93 patterns. That is the definition of working smarter, not harder.
It really is.
You literally cut the computational latency in half. In an optical router processing terabits per second, cutting the workload by 50% is a colossal saving in power consumption, heat generation, and silicon real estate.
And in figure 3, they plot the list error rate against the total number of patterns used at a fixed signal-to-noise ratio of 5.5 dBs. It shows a diverging, widening gap. As you allow the receiver to use more patterns, MCOC and logistic weights drop the error rate exponentially faster than the chase variance. The smarter the algorithm gets, the further it leaves the legacy systems behind.
That is a very satisfying graph. Section 6 is the conclusion, summarizing their findings and acknowledging Benjamin Castells for pointing them to efficient order statistics calculations. So, summarizing the main body of the paper. The MCOC algorithm uses a brilliant proxy of distance to map out the highest probability areas to search for errors, and it does so with less than half the computational effort of legacy systems, directly saving power and money in real-world optical networks. So, summarizing the main body of the paper. Final completeness check for the main text. Are we perfectly aligned on the core narrative before we plunge into the deepest part of the math?
I believe we are. The engineering problem has been completely solved and validated. But honoring the unabridged protocol, we are not done. We need to look at the appendices. We need to look at how they actually proved the theorems that allowed all this.
The deepest dive. Section A, the appendices. Appendix A provides the formal mathematical proof of Lemma 1, which we discussed earlier. They want to rigorously prove that the set of error vectors covered by a new pattern is exclusively defined by a specific set of indices, which they call V sub 1. To do this, they define 3 subsets. Let's break them down.
Sure. Subset V1 involves errors in positions more reliable than the maximum index of the pattern. Subset V2 involves error vectors with a total Hamming weight less than the decoder radius t. And subset V3 involves error vectors within the positions up to the maximum index.
So they have partitioned the space.
Exactly. I love how clean this proof is. It's a classic textbook proof by exhaustion. They systematically eliminate V2 and V3 to show that only V1 can be the new covered space.
How do they eliminate V2?
They prove V2 is already covered by previous patterns because of property 1. Remember, patterns with smaller Hamming weights are always generated earlier in the logistic weight sequence, so V2 is old news.
And a V3.
They prove V3 is already covered because any pattern with the same Hamming weight, the smaller binary representation, was also generated earlier. By exhausting all other mathematical possibilities, only V1 remains. It's structural deduction at its finest.
Completeness check on Appendix A. Does proof by exhaustion make sense here?
It does. It strictly confines the new covered space. Let's proceed to Appendix B.
Moving to Appendix B, this is the order statistics setup. This is where the terrifying continuous math lives. We are looking at the probability density functions. They define f sub c of x and f sub e of x as the density functions of the reliability for a correct hard decision and a wrong hard decision, respectively.
Right. Remember, the reliability is a continuous variable based on the physical voltage. These functions describe the shape of the bell curve for those reliabilities.
Let's execute the pronunciation protocol for equation 11. Equation 11 defines the density function for a correct hard decision. It is written as f6cx, frac u sigma x plus 1, text for x, shape q0, vocalized as f sub c of x equals q sub sigma of x plus 1 over q sub sigma of 1 for x greater than or equal to 0.
Perfect. Instead of spelling out the syntax further, let's explain the mechanism of equation 11. It is the math version of a shifted bell curve. Because we are operating under the condition that we know the bit was guessed correctly, the equation physically shifts the center of that bell curve away from 0, pushing it towards our expected positive or negative voltage.
And the denominator?
The denominator of the equation simply normalizes the area under the curve, scaling it down so the total probability still equals exactly 100%. It reshapes the curve based on our confidence.
And equation 12 defines the density function for a wrong hard decision. The mechanism is the exact same logic, but the bell curve is shifted in the opposite direction, towards 0, because the noise overpowered the signal and caused an error.
Right, it pulls the distribution into the error zone.
So we have the baseline density functions, but then we get to equations 17 and 18, which define the joint probability density functions. These equations are massive. They span multiple lines of factorial products. Why so huge?
Think back to the dice analogy. If I want the probability that the highest die is a 6, that's a single-order statistic. It's relatively simple. But if I want the probability that the highest die is a 6, and the second highest is a 5, and the third highest is a 4, that is a joint-order statistic.
Oh, I see.
Because all the variables are dependent on each other's sorting order, you get these massive product summations with factorials to account for all the different permutations. It is a literal combinatorial explosion.
To ground this explosion, the authors provide a brilliant step-by-step toy example. Example 1. They use a tiny, simplified 7/4 Hamming code with an error correction radius of t equals 1, and they use 19 logistic weight patterns. They want to calculate the added probability of a single specific pattern. The pattern is 1, 1, 0, 1, 0, 0. Let's actually walk through this live right now to see how the math translates to physical reality.
Let's track it carefully. The pattern has a Hamming weight of 3 because there are 3 ones in the vector. If we look at the positions of the ones, they're index 1, index 2, and index 4. So the maximum index of an error is position 4.
They state that to find the probability that the error vector exactly matches this pattern up to position 4, given that there are exactly 5 total errors in the channel overall, we have to translate the ones and zeros into mathematical conditions on the sorted reliabilities. They use variable beta to represent the reliability of errors and variable gamma to represent the reliability of correct bits.
This is the Rosetta Stone of the entire appendix. They are translating a discrete sequence of bits into a set of continuous inequality constraints.
Okay.
Look at the pattern. 1, 1, 0, 1. It dictates the physical reality of the voltages. The first 2 positions are 1s, meaning they are errors.
Okay.
So the first 2 errors, beta 1 and beta 2, must have lower reliabilities, meaning they're closer to the 0 voltage threshold than the first correct bit, gamma 1.
Then there is a 0 at position 3, meaning it's correct.
Right. Then there's a 1 at position 4. That is our third error, beta 3. This third error must have a higher reliability than the first correct bit, but it must have a lower reliability than the second correct bit, gamma 2.
Wow. It maps a simple sequence of binary choices into a multi-dimensional geometric shape of constraints. They label this constraint space F.
Exactly. The bit pattern defines the walls of a multi-dimensional box.
And finally, equation 19. They state the conditional probability can be calculated by an integral over this constraint space F.
But calculating a multi-dimensional integral over a complex, shifting constraint space like F is analytically torturous. It is the kind of calculus that literally breaks computers, which leads to their final, most elegant trick in the entire paper: efficient Monte Carlo integration.
They explain that instead of trying to solve the integral algebraically, they use the beta distribution built into standard math libraries. They draw random samples from a uniform distribution, use the inverse cumulative distribution functions to generate ordered variables, and then they just check if those variables fit inside the walls of F.
It is so computationally satisfying. They bypass the impossible calculus entirely. They generate valid statistical universes and simply count how many of them fit inside the boundary conditions dictated by the bit pattern. It's numerical integration at its finest, made hyper-efficient by leveraging standard statistical libraries.
Okay, doing a final synthesis check of the entire unabridged protocol. We covered the history of chase decoding, the physical realities of AWGN channels, the geometry of Hamming balls, the efficiency of the MCOC distance checking algorithm, and finally, the translation of bit patterns into continuous integrals solved by Monte Carlo sampling. Are we leaving any mathematical stone unturned?
I believe the protocol is entirely complete. We have walked the path from the physical layer of voltages all the way up to multidimensional numerical integration, and we understand how every single piece fits together to achieve that 0.2 dB gain.
Congratulations to you, our listener, for surviving this deep dive. You made it. We journeyed from the absolute basics of why binary codes are used in modern telecom, walked through the geometric analogies of flashlights and dark rooms, and plunged into the combinatorial depths of order statistics. We learned how replacing a rigid legacy algorithm with a heuristic maximum covering ordered candidate algorithm can cut the computational burden in half, saving massive amounts of power in data centers while actually improving error rates.
It is a true masterclass in applying probability theory to structural engineering. By understanding the specific shape and physics of the noise, the authors designed a net perfectly contoured to catch it.
But I want to leave you with a final thought to mull over, extending beyond the scope of this paper. We have spent all this time optimizing test patterns for binary symmetric channels and additive white Gaussian noise. Our entire assumption today is that a bit is a discrete classical entity, a 1 or a 0, corrupted by a continuous physical wave. But as we move toward the horizon of quantum communication, well, when we start transmitting qubits through entirely new physical channel models, how will the definition of reliability and distance change?
It raises an incredible paradigm shift. In a quantum channel, a qubit can exist in a superposition of both 0 and 1 simultaneously. The noise isn't just additive thermal variance shifting a voltage, it's quantum decoherence collapsing a state. Will the concept of logistic weights, penalizing specific index positions, even hold up when the fundamental unit of information isn't strictly binary anymore? We might need entirely new, non-Euclidean geometries to even define what a covered space is.
It's a fascinating frontier. The flashlights and dark rooms of tomorrow are going to look very different. But for today, the math holds firm. Taking the time to truly understand this math, line by line, concept by concept, is the ultimate shortcut to being well-informed. Because when you understand the mechanics beneath the abstract numbers, the magic disappears and the mastery begins. Thanks for joining us in the depths. Imagine for a second that you could save millions of dollars in electricity. Like you could just slash the thermal output of a hyperscale data center and speed up the internet globally just by tweaking a mathematical algorithm so it performs 0.2 decibels better.
Right, which sounds completely absurd when you say it out loud. A fraction of a decibel.
Exactly. It's the equivalent of turning the volume dial on your stereo a fraction of a millimeter. I mean, you wouldn't even hear the difference.
You really wouldn't. But, in the hidden world of advanced telecommunications, people dedicate years of their lives to fighting for that microscopic margin.
They really do. So welcome to the deep dive. Today, you are embarking on an auditory marathon. We are looking at a paper that does exactly that, and we are not holding back.
No, we are definitely not. We are executing what we call the unabridged protocol today.
Right. For those who know, the unabridged protocol means linear progression only. We go line by line, paragraph by paragraph, formula by formula, no skipping ahead.
We are dissecting a paper titled Chase-like Decoding, Test Pattern Design and Performance Analysis. It comes to us from Tim Janz, Simon Obermüller, Andreas Zunker, and Stephan Brink.
And they are all from the University of Stuttgart in Germany. So the mission of this deep dive is to uncover exactly how these researchers pulled off that 0.2 dB gain.
Yeah, because they didn't do it by inventing new fiber optic cables or, new lasers. They did it purely through math.
Right, using a strategy called optimal test pattern sets. So we're going to leave absolutely no mathematical stone unturned here. But before we get to the very first sentence, I need to initiate our first completeness check.
Go for it.
Does that fully unpack the title, the authors, and our core mission? Or have we missed any nuances here?
I think we've thoroughly unpacked the introduction. The stage is set. We can officially jump into the abstract.
Perfect. So let's start with the very first sentence of the abstract. The authors state that chase-like decoding algorithms are a popular choice for, quote, soft input decoding of algebraic codes.
Right, so we have to stop right there and define soft input decoding fundamentally. Because if you don't grasp that, the rest of the paper is just noise.
Yeah, let's break it down. What does soft input mean compared to, say, a hard decision?
Well, imagine you're listening to someone mumble a word from across a noisy room. A hard decision is forcing yourself to just write down exactly what you think they said, yes or no.
Right, even if you're only 55% sure they said yes, you just write yes. The nuance is gone.
Exactly. In a standard digital receiver, the hardware looks at an incoming analog electrical voltage. Let's say a binary 0 is a positive voltage, and a binary 1 is a negative voltage.
But because it travels through miles of copper or optical fiber, it picks up thermal noise.
Yeah, additive white Gaussian noise.
Mm.
So the receiver doesn't get a clean +1 or -1. It gets a messy, maybe negative 0.2 volts.
And a hard decision decoder just looks at that and says, well, it's negative, so it's a 1. End of story.
Precisely. But a soft input decoder is way smarter. It retains a confidence metric. It says, my best guess is a 1, but I am very, very unsure because it's so close to 0.
Okay, that makes sense. So that covers the first sentence. Now, the next sentence in the abstract mentions order statistics, covered space probabilities, and Monte Carlo integration.
Yeah, the authors are laying out the 3 specific tools they use to evaluate these test patterns.
Right, and we have the why mandate here. Why mention these 3 specific things right up front?
Because evaluating how well a decoding algorithm works is historically a massive computational bottleneck. They are signaling to the reader immediately that they have solved the measurement problem before they even introduce the optimization problem.
Ah, okay. So they're establishing credibility. Then we hit the final sentence of the abstract where they claim their new algorithm yields performance up to 0.2 dB better than conventional restricted chase decoding.
And that is the mic drop of the abstract.
Right. But again, why does 0.2 dB matter? We mentioned it in the intro, but let's dig deeper into the physical reality of that.
Well, think about a hyperscale data center. You have hundreds of thousands of servers communicating constantly. Decibels operate on a logarithmic scale.
Meaning it's a ratio of signal power to noise power?
Exactly. A 0.2 dB improvement in coding gain means the lasers firing the light pulses can be slightly less powerful, or you can push the data just a tiny bit faster without increasing errors.
And when you multiply that tiny power saving across millions of servers, it's massive.
Massive reductions in thermal output, huge financial savings. It is a highly coveted margin in telecommunications.
Okay, that is a fantastic foundation. So completeness check, does that fully deconstruct the abstract?
Yes, I believe we have extracted every bit of context from the abstract. We can move to paragraph 1 of the introduction.
Awesome. So paragraph 1 of the intro explicitly mentions binary Bose Chaudhuri Hocquenghem codes, or BCH codes.
Right. And before we go further, we need to digress into what a block code actually is, structurally speaking.
Yeah, please. I know they break data into chunks, but how does the math actually work?
So imagine you have a chunk of raw data, say a k-bit block. A block code takes that and mathematically weaves in extra redundant bits to create a larger block of no bits. We call this an no-calo code.
And those extra bits aren't just dumb copies, right? They are calculated using abstract algebra.
Exactly. They use Galois fields to create a rigid mathematical structure. So if noise flips some bits, the receiver can use that underlying structure to pinpoint the errors and flip them back.
I always think of it like a dictionary. If my dictionary only has the words cat and dog, and a typo changes cat to bat, I know bat isn't a valid word. And since it's closer to cat than dog, I fix it to cat.
That is the perfect analogy for Hamming distance. The number of letters you change is the distance. BCH codes guarantee a specific minimum distance between all valid code words.
Right. And paragraph 1 also lists real-world applications. They mention concatenated coding schemes, the KP4 Reed-Solomon code for Ethernet, and OFEC for long-haul optical communication.
Yeah, they are pointing out that BCH codes are often used as the inner code in a belt and suspender setup. The inner BCH code cleans up the worst noise quickly, and an outer code catches the rare slip-ups.
Okay, completeness check on paragraph 1 of the introduction. Have we thoroughly unpacked the context of BCH codes and their applications?
I'd say we've nailed it. We can proceed to paragraphs 2 and 3.
Great. So paragraphs 2 and 3 contrast hard decision decoding, HDD, with maximum likelihood decoding, ML. We touched on this, but let's formalize the gap they're describing here.
Sure. HDD is like your dictionary analogy. It's rigid and ultra-fast, but it ignores soft input reliability, so it leaves performance on the table.
And ML is the opposite extreme.
Right. ML compares the received noisy signal against every single possible valid code word in the entire dictionary, picking the absolute best statistical match.
But the dictionary for a long code has like trillions of valid words, so ML is physically impossible to compute in real time.
Exactly. So the telecommunications industry has this massive gap, and that is where chase-to-taken decoding comes in, which paragraph 3 introduces.
How does chase-to-taken actually work? The paper says it generates a list of candidate code words, lol or dollars, from decoding 2 PETA test words.
So David Chase realized you don't need to check the whole dictionary. You sort the received bits by how reliable they are. You find the least reliable bits.
The ones hovering closest to that 0-volt threshold?
Yes. You isolate them, and you flip every possible combination of those PD bits that generates 2 PETA test words. You feed all of those into the fast, rigid HDD decoder.
Oh, I see. You're basically tricking the fast decoder by feeding it multiple what-if scenarios based only on the sketchiest bits.
Exactly. The decoder spits out a short list of valid candidates,
Right.
and you just pick the best one. It gives you near ML performance with HDD speed.
That's brilliant. And the end of paragraph 3 mentions GRAND, guessing random additive noise decoding, and logistic weights. What is that?
GRAND is a newer algorithm. The key takeaway here is the concept of logistic weight, which penalizes flipping highly reliable bits. We will see the exact formula for this in the preliminaries.
Okay, I'm holding you to that. Completeness check for paragraphs 2 and 3. Have we fully established the problem and the chase-to mechanics?
Yes, the gap between HDD and ML is clear, and the chase-of bridge is established. We can hit paragraph 4.
All right. Paragraph 4 starts with the word furthermore.
Yeah, that is a massive rhetorical pivot.
Right, because up until now, they've just been describing existing tools, but furthermore signals the presentation of their novel contribution.
Exactly. They are stating that furthermore, they're going to present 3 specific list error rate, or LER, evaluation methods, and introduce their brand new pattern design algorithm.
It's the roadmap for the rest of the paper. Completeness check on paragraph 4. Have we analyzed its rhetorical purpose and transition?
We have. The introduction is now fully complete. We are stepping into section 2, the preliminaries.
Okay, section 2. This is where we define the mathematical universe. Let's go through the notation paragraph with extreme granularity. They define index sets, power sets, and indicator vectors.
Right. They start by defining an index set $. The power set, denoted as script P of K, is simply the set of all possible subsets of dollars.
Okay, and then they talk about subvectors and the indicator vector.
Yeah, an indicator vector, denoted as dollars, is just a binary string where there's a 1 at every index position that's inside the set dollars and a 0 everywhere else.
Got it. And they mention element-wise addition over the finite field, math BBF to 2. That's basically just XOR logic, right? 1 + 1 = 0.
Precisely. Now, we absolutely must execute the perfect pronunciation protocol for the logistic weight formula they introduced right after the Hamming distance definition.
Yes, let's do it. So this is the formula that penalizes flipping reliable bits.
Correct. The paper defines the logistic weight formula. The latex is WLU, sum I 1n IUY. WI sub L of U equals the sum from I equals 1 to n of I times U sub I.
Okay, let's unpack why this formula works. We is just a binary value, 0 or 1, indicating if a bit is flipped.
Right, and you multiply it by $, which is its index position. Remember, we sort the bits so position 1 is the least reliable and position $, is the most reliable.
Ooh, so if I flip the bit at position 1, $, is 1 times 1, so it adds 1 to the weight. But if I flip the bit at position 100, it adds 100 to the weight.
Exactly. It makes mathematically dangerous guesses inherently heavier.
That is so elegant. Okay, complete mischeck on the notation paragraph. Have we defined the universe and executed the protocol for logistic weight?
Yes, the foundational math is locked in. We can move to part A of the preliminaries, the channel model.
All right, part A. They define the BIAWGN channel. Binary input additive white Gaussian noise.
Right. This is the mathematical model of the messy real world we talked about earlier.
And they immediately hit us with a formula for the probability of $B bit flips occurring during transmission. We need the perfect pronunciation protocol here.
Absolutely. The paper defines the probability of $B bit flips in equation 1. The latex is PEB by num NB 1Q1 sigma BQ1 sigma NB. Capital P of E sub B equals N choose B times the quantity 1 minus capital Q of 1 over sigma raised to the power B times capital Q of 1 over sigma raised to the power N minus B.
Okay, wow. Let's break that down. What is this capital Q function?
The Q function gives you the tail probability of the standard normal Gaussian distribution. Basically, it calculates the exact odds that the random noise is strong enough to push the voltage across the zero threshold, causing an error.
Right, so Q tolerates the probability of a single bit being flipped by noise, where sigma is the noise variance.
Yes, so the formula just calculates the combinations. D choose the null ways the errors can happen, times the probability of B dollars occurring, times the probability of the remaining minus B dollar bits staying correct.
That makes perfect sense. Now, there's a sentence right after this that caught my eye. They state, "We assume that the received channel output is already sorted." Why explicitly state that?
Because it's the foundational strategy of chase decoding. You absolutely must sort the bits from least reliable to most reliable before you do anything else. By stating it as an assumption here, they simplify all the math that follows.
Ah, okay. Then they give us the probability of the bounded distance decoder failing. Let's protocol that.
Right. The paper defines the probability of successful bounded distance decoding in equation 2. The latex is PBDD, PAT, capital P sub BDD equals the sum from J equals 0 to T of capital P of E sub J.
So 2 errors is the maximum number of errors the dictionary can guarantee fixing. So this just adds up the probabilities of getting 0 errors plus 1 error all the way up to 2 errors.
Exactly. If the number of errors is less than or equal to 2, the BDD succeeds. Anything more, and it fails.
Beautiful. Completeness check on part A, the channel model. Have we unpacked the AWGN model and both equations?
I believe we have. The channel is fully modeled. Let's move to part B, chase-like decoding.
Right. So part B starts by walking through the exact steps of obtaining a hard decision, cis.IT, generating a set of test words, which they call script T, and leading them to the BDD.
Right, which we conceptually discussed, but here they define it formally. The most important part of this section is how they distinguish between different types of pattern sets.
Yeah, they define classic chase2 patterns, which they denote as script R sub chase. This is flipping every possible combination of the least reliable bits.
But then they introduce restricted chase patterns, script R sub res. Why do we need restricted patterns?
Well, as we mentioned earlier, flipping all 8 bits simultaneously in a small window is statistically super unlikely. So restricted chase puts a hard cap on the Hamming weight. It says you can pick combinations from the worst bits, but you can't flip more than, say, 3 bits at a time.
Precisely. It prunes the useless test patterns. And then we get to the core definition of the paper. We need to analyze definition 1 logistic weight patterns word for word.
Okay, let's look at definition 1. It basically states that a logistic weight pattern set is formed by simply choosing the dollar patterns that have the absolute lowest logistic weight.
Right. And remember the logistic weight formula we discussed. It forces the algorithm to explore the unreliable zone first.
But the definition also includes a very strict tie-breaking rule. What happens if 2 different patterns calculate to the exact same logistic weight?
It's a great question. Let's say flipping bit 3 gives a weight of 3. And flipping bits 1 and 2 also gives a weight of 1 plus 2, which is 3.
Right. Which one gets priority?
The definition explicitly says you first resolve ties by picking the pattern with the lower Hamming weight. So flipping just bit 3, which is a Hamming weight of 1, beats flipping bits 1 and 2, which is a Hamming weight of 2.
That makes total statistical sense. Fewer total errors are more likely. And if there's still a tie after that...
Then they just use the integer value of the binary representation to break the tie. It ensures the set generation is completely deterministic. Every time you run it, you get the exact same optimal set.
Amazing. Okay, completeness check on part B. Have we thoroughly defined the decoding steps and the specific pattern sets?
We have. The pattern definitions are locked. We can proceed to part C and D, error probability and covered space.
Excellent. This section is mathematically dense. Let's start with the mathematical decomposition of the error probability and define the list error rate.
Right. The paper decomposes the total probability of an incorrect decoding. They show it is fundamentally bounded by 2 things. First, the theoretical limit of the code itself, meaning noise, pushed the signal into a completely wrong but valid Hamming ball.
Which you can't fix because the laws of physics say it looks like a valid code word.
Exactly. And the second part is the list error rate, or LER. This is the probability that the correct code word simply fails to make it onto the shortlist generated by the test patterns.
So the LER is the only thing the researchers have the power to shrink. Now we have equation 3. Let's protocol it.
The paper defines the probability of an error vector given the received signal without codebook information in equation 3. The latex is PV, Y. Capital P of V given Y equals the product from I equals 1 to N of capital P of V sub I given I sub I.
Okay, this just means if we ignore the dictionary rules, the probability of a specific error vector is just the multiplied probabilities of each individual bit being wrong based on the raw voltage.
Right, assuming independence, which is standard. Then they move to the covered space concept. We talked about the geometric analogy earlier.
Right, the infinite field with flagpoles, and we are dropping nets, the Hamming balls over it. Let's protocol equations 4 and 5, which formalize this.
Yes, the paper formally defines the covered space in equation 4. The latex is mathcal v in mathcal bix and mathcal x. The covered space script v equals the union over all x in script t of the Hamming ball script b sub d at x.
Okay, so script v is just the total overlapping volume of all the individual nets we dropped.
Precisely. And then equation 5 calculates the probability of that volume. The latex is p, and it's called v, dv. Capital P of script v equals the integral over script v of f of v dv.
So you just integrate the probability density function over that complex, lumpy, overlapping shape to find out how likely it is that the true error falls inside our nets.
That's exactly it.
Right.
And that integration is a nightmare to calculate, which sets up the rest of the paper.
Yes, it does. Okay, completeness check on parts C and D. Have we decomposed the error probability and fully defined the covered space equations?
We absolutely have. That concludes the preliminaries. We are now entering section 3, performance evaluation methods.
Section 3. This is where they actually calculate the list error rate. Let's start with how they define added probability, because this is a crucial concept.
Right. If you have a set of patterns and you decide to add one more pattern to the set, you need to know how much new probability volume you just captured.
Let's protocol equation 6 for this.
The paper defines the added probability in equation 6.
Yeah.
The latex is pad, p, mathcal b new. Capital P sub add equals capital P of the set difference of script v sub new and script v sub old.
So you take the new total volume and you literally subtract the old volume, so you are only left with the brand new territory that the new pattern claimed.
Exactly. It's the marginal utility of the new test pattern.
Okay, completeness check on the added probability definition. Are we good?
Yes, that is fully unpacked. Now we dive into part A, list error rate with order statistics.
Okay, this is the heavy math. Let's digress into a foundational explanation of what order statistics are. We used the dice analogy before, right?
Yeah, let's revisit that. If you roll 5 dice, the probability of the first die being a 6 is 1 in 6. Standard independent probability.
But if you roll them, sort them from lowest to highest, and then ask the probability of the last die being a 6, it changes everything.
Right, because sorting destroys independence. The position of a variable now dictates its relative value to all the others. Order statistics is the branch of math that gives us the density functions to calculate probabilities after sorting.
And since the Chase decoder explicitly sorts the received bits by reliability first, we have no choice but to use order statistics.
Precisely. You cannot use standard probabilities on sorted bits. It will give you wildly wrong answers.
Okay, so let's look at equations 7 and 8. Let's protocol them.
The paper defines the list error rate for Chase 2 in equation 7. The latex is LERC equals 1P math and Cal VC. LER sub C equals 1 minus capital P of script V sub C.
And equation 8 is for restricted Chase.
Yes, the latex is LERR equals 1P math and Cal VR. LER sub R equals 1 minus capital P of script V sub R.
Okay, logically, these just state that the error rate is 100% minus the probability that our nets caught the error. It's the probability of missing.
Exactly. But how do you calculate the probability of the nets catching the error using order statistics? That's what property 1 and lemma 1 are about.
Let's look at property 1. It mentions a sequential implementation trick. I love this part.
Oh, this is brilliant hardware engineering. Remember how we said the decoder has to calculate a syndrome to check if a test word is valid?
Yeah, and doing that from scratch for a huge code word takes a lot of logic gates.
Right. Well, property 1 states that if you generate your test patterns using the logistic wait sequence, the next pattern in the list almost always differs from the previous pattern by only a single bit flip.
Wait, really? Just one bit difference?
Usually, yes.
Yeah.
Which means you keep the old syndrome in memory. When the new test word arrives, you just do one single XOR operation for the one bit that changed.
Wow. So you instantly have the new syndrome without recalculating the whole thing. That is a massive speed up on the silicon chip.
It is. It makes the logistic wait patterns incredibly attractive for hardware designers.
Okay, let's move to lemma 1 and the overarching proposition 1, which ties us together with the added probability. Let's protocol equation 9.
The paper formally states proposition 1 in equation 9. The latex is LER key day check LER Q1 pad Q. LER sub Q equals LER sub Q minus 1 minus capital P sub add comma Q.
Let me trace the logic here. The list error rate of having telerap patterns is equal to the error rate of having telara -1 patterns minus the new probability volume captured by the telara pattern.
You nailed it. It's an induction proof. You start with the baseline error rate, and every time you add a carefully chosen test pattern, you mathematically subtract its marginal utility from the error rate, driving it closer to zero.
And because they use order statistics, they can calculate that marginal utility, that added probability, incredibly accurately without having to map out the n-dimensional geometric overlapping spheres.
Exactly. It bypasses the combinatorial explosion of the geometry.
Incredible. Completeness check on part A, order statistics. Have we fully decompressed the math and the sequential trick?
I believe we have thoroughly unpacked it. We can briefly touch on parts B and C, covered space, and Monte Carlo.
Right. So we know the cover space calculation is mathematically exact, but geometrically a nightmare. Let's look at the Monte Carlo method in Part C protocol equation 10.
The paper defines Monte Carlo integration in equation 10. The latex is P approx 1n, sum K1 IVK in MathCalV. Capital P is approximately equal to 1 over n times the sum from k equals 1 to n of the indicator function I of v sub k in script v.
So Monte Carlo is the brute force way. $1 is the number of simulations. You just run millions of random tests, and the indicator function acts as a counter, keeping track of how many times the error lands in our covered space.
Right. You just count the successes and divide by the total attempts. It requires zero complex math.
But the text explicitly says it's computationally expensive at high SNRs. Why does a clean signal make the simulation harder?
Because if the channel is very clean, errors are incredibly rare. If the true error rate is 1 in a billion, you might have to simulate 100 billion messages just to observe a statistically significant number of failures.
And running a complex decoder simulation 100 billion times would take server farms weeks to finish. So Monte Carlo hits a wall for high-end optical networks.
Exactly. That is why they had to develop the order statistics method.
Okay, completeness check on parts B and C. Have we explained the Monte Carlo equation and its limitations?
Yes, the evaluation tools are completely covered. Now we pivot to section 4. Pattern designs for chase-like decoding. This is where they actually try to build the optimal set.
All right, section 4, the active problem. They define the optimal set, script R subopt, as the one that minimizes the LER. But they immediately say that maximizing submodular set functions is NP-hard.
Yeah, that's a term we hear a lot, but we need to explain what NP-hard actually means for a listener who isn't a computer scientist.
Right, let's break it down. It relates to combinatorial explosion.
Yes. Think of the traveling salesman problem. If a salesman visits 5 cities, there are 120 possible routes. A computer can check that in a millisecond.
But if he visits 50 cities, the number of routes is astronomically large, like more than the atoms in the universe.
Exactly. There is no mathematical shortcut to finding the absolute best route. You just have to check them all. And for this paper, picking the absolute best combination of 42 test patterns out of thousands of possible bit flips creates the exact same explosion.
So a supercomputer can't just brute force the perfect set, even for a code with just 256 bits.
It is computationally intractable. It's a mathematical dead end.
Okay. Completeness check on the optimization problem and NP hardness. Is that clear?
I think the sheer impossibility of brute force is very clear. Let's move to parts A and B, generating candidates and the greedy pattern design.
Right. So if we can't find the perfect set, we have to find a good enough set.
Yeah.
Enter the greedy algorithm.
The greedy algorithm is a classic heuristic for NP-hard problems. It makes the best local choice at every step without looking ahead.
Walk me through how that applies to test patterns.
It starts with an empty set. It searches every possible pattern and finds the single one that covers the most probability volume. That's pattern 1.
Okay, makes sense.
Then, it searches the remaining space to find the pattern that adds the most new, non-overlapping volume to pattern 1. It greedily grabs the biggest remaining chunk, and it repeats this until it has dollar patterns.
But the paper mentions a trick to speed this up, using an ordered candidate pattern algorithm, or OCP.
Right. Before the greedy algorithm starts, OCP pre-sorts all the candidate patterns by their absolute maximum volume.
So it creates a ranked list of the biggest nets available.
Exactly. So when the greedy algorithm is searching for the next edition, it goes down this sorted list. As soon as it checks a pattern whose total maximum volume is less than the added volume of the best pattern found so far in that step, it stops.
Because it knows with mathematical certainty that nothing further down the list could possibly be better.
Right. It drastically reduces the search space. But here's the kicker.
The authors admit that even with the OCP trick, the greedy algorithm is still too slow for real-world optical fiber codes.
Because at every single step, it still has to calculate those complex n-dimensional overlapping spheres for the top candidates.
Yes, it's a great theoretical benchmark, but it's not a practical engineering tool.
Okay, completeness check on the greedy algorithm and OCP. Have we tracked the logic and its limitations?
We have, which brings us to Part C, the climax of the paper. Maximum Covering Pattern Design, or MCOC.
MCOC. This is how they actually achieve the 0.2 dB gain in the real world. What is the fundamental premise here?
MCOC ditches the complex calculus of overlapping spheres. It relies on two simplifying heuristics. First, a good pattern set absolutely must cover the most highly probable error vectors.
Right, you have to patch the biggest holes first.
Second, the raw probability of a single error vector is a good enough proxy for the total volume of the Hamming ball surrounding it.
Okay, let's walk through algorithm 1, the MCOC algorithm, sequentially. I have a visual analogy for this.
Let's hear it.
Imagine you walk into your kitchen and there's a massive, uneven puddle of water on the floor. You only have 42 paper towels, and your goal is to absorb maximum water.
Okay, so the puddle is the probability space, the deepest parts are the highly probable error vectors, and the paper towels are your test patterns, the Hamming balls.
Exactly. Now, the greedy algorithm would pause and mathematically model the fluid dynamics and overlap absorbency of every possible placement before dropping a towel. It takes forever.
Right. So what does MCOC do?
MCOC looks for the absolute deepest part of the puddle, the single most likely error. It asks, is a towel already covering this? If not, it's exposed.
And we must cover it. But we don't just blindly drop a towel dead center.
Well, right. You're smarter than that. You carefully position the center of a new towel over the thickest part of the water nearby, ensuring its edge reaches over to cover that deep spot. But its center also absorbs maximum water from the surrounding area.
That is a phenomenal translation of the algorithm. Line by line, algorithm 1 grabs the most likely error pattern from the OCP list. It checks the minimum Hamming distance to the patterns already in our set.
And if that distance is greater than the correction radius $, the error is exposed.
Exactly. So it searches back up the list of highly probable patterns. It finds the most likely pattern that is still within distance $2 to the exposed error, and it adds that one to the set.
It guarantees coverage of the weak spot while maximizing overall probability capture. And it does it just by checking Hamming distances, not calculating geometric volume.
Which is why it runs in polynomial time. It is incredibly fast.
That is brilliant engineering. Completeness check on Part C, the MCOC algorithm. Have we unpacked the heuristics and the paper towel analogy?
Yes, the core mechanism of their breakthrough is fully deconstructed. We can transition to Section 5, Results, Conclusion, and Appendices.
Let's look at the data. They start by analyzing Figure 1, which uses a smaller 128/120 extended Hamming code.
Right. This is their validation check. They plot the list error rate using the slow Monte Carlo, the complex covered space, and their fast order statistics method.
And all three lines perfectly overlap on the graph.
Which proves mathematically that their fundamental equations are completely rock solid. Order statistics predicts the LER flawlessly.
Okay, then they put the different pattern sets into the arena. Classic chase, logistic weights, the heavy greedy algorithm, and the new MCOC.
And they fix the allowed patterns to 16 and then to 64.
What are the results?
Classic chase performs the worst, as expected. The greedy algorithm technically wins, which makes sense since it's the computationally heavy benchmark.
But MCOC is right there, isn't it?
Yes, MCOC is practically indistinguishable from the greedy algorithm on the graph, but it generated the set in a fraction of the time. Also, the logistic weight patterns perform admirably well, showing only a tiny drop in performance.
That's a huge win. But the real test is figures 2 and 3. They apply this to the 256, 239 extended BCH code.
Right, which is not a toy example. That is the exact component code used in OFEC, the standard for transoceanic optical fiber.
And here is the massive reveal. The text states, surprisingly, the MCOC patterns with 2 lambda equals 42 perform better than the restricted chase patterns with more than twice as many test patterns.
Right. Let that sink in. MCOC with 42 patterns beats the industry standard of 93 patterns.
That is a tectonic shift in hardware design.
It really is. You have literally cut the complexity of your decoder by more than half. You can process data twice as fast, using half the silicon area and consuming half the power.
And despite doing half the work, because the patterns are so deeply optimized, you actually patch more errors. This is where the 0.2 dB gain translates into millions of dollars. It's just a beautiful example of how deep abstract math directly impacts physical human infrastructure. Completeness check on the results section. Have we fully analyzed the data points in the massive 42 versus 93 win?
We have. The results are undeniable. We can quickly deconstruct the final summary paragraph of the conclusion.
Right. The conclusion essentially states they built a complete toolkit. They proved order statistics accurately predict performance, avoiding the Monte Carlo trap at high SNRs.
And they delivered MCOC, a fast algorithm that solves an intractable NP-hard problem well enough to shatter existing industry standards.
Completeness check on the conclusion.
The conclusion is fully parsed. Now, to truly execute the unabridged protocol, we must tackle Appendix A and Appendix B.
Okay, deep breath. Appendix A is the proof of Lemma 1. Let's break this down. They define 3 distinct volume spaces, script V sub 1, V sub 2, and V sub 3.
Right. This is where they logically deduce why the total covered space is the sum of these partitions. V sub 1 is the volume covered exclusively by the older patterns.
Okay, V sub 2 is the volume covered exclusively by the new pattern we are adding.
Yes, and V sub 3 is the intersection, the volume covered by both the old patterns and the new pattern.
So by defining these strict partitions, they mathematically prove that the new added probability is simply V sub 2 without double counting V sub 3. It's a rigorous set theory proof to back up their added probability formula.
Exactly. It's watertight logic.
Okay, completeness check on Appendix A.
Proof confirmed. Let's hit the final section, Appendix B, which is a dense forest of order statistics setup.
Right. This is formula heavy. They define the density functions for a correct bit and a wrong bit. We need to protocol equations 11, 12, 13, and 14. Let's start with 11 and 12, the probability density functions.
Absolutely. The paper defines the density function for an erroneous bit in equation 11. The latex is frak1 squazi 2, frat1 2, f sub e of x equals 1 over the square root of 2 pi sigma squared times e raised to the power of negative, the quantity x minus 1 squared over 2 sigma squared.
Okay, that's the standard Gaussian bell curve, just shifted to center around a mean of positive 1 representing the error. Let's do equation 12.
Right. Equation 12 is the density function for a correct bit. The latex is f standard fry 1 plus 1 2 sigma f sub c of x equals 1 over the square root of 2 pi sigma squared times e raised to the power of negative quantity x plus 1 squared over 2 sigma squared.
So that one is centered around -1. Now, order statistics require the cumulative distribution functions, the CDFs. Let's protocol equations 13 and 14.
The paper defines the CDF for an error in equation 13. The latex is FVX in infinity CT. And f sub ESX equals the integral from -infinity to x of f sub e of t dt.
And equation 14 is the CDF for the correct bit.
Yes. Latex is FCX FCT dt. Capital F sub CX equals the integral from -infinity to x of f sub c of t dt.
Okay, so they have all the integrals set up. Then they introduce the variables beta and gamma. What do these represent in the math?
Beta variables represent the reliabilities of the bits that were actually flipped by noise.
Yeah.
Gamma variables are the reliabilities of the correct bits.
And they walk through example 1, a toy example, using the small 7, 4 Hamming code, to show how these interact when sorted.
Right. They assume a pattern flips 3 bits, but say a total of 5 errors actually occurred during transmission. Because all bits are globally sorted by reliability, the math forces strict boundaries.
Oh, I see. They state the condition 30 Wallers 1, meaning the reliability of the worst correct bit has to strictly be higher than the reliability of the best wrong bit inside that specific sorted window.
Exactly. The integral they solve calculates the multidimensional volume where those specific boundaries do not cross.
But solving a multidimensional integral with pure calculus for hundreds of variables is agonizing.
It is, which brings us to the final calculation rule. They use a software engineering trick. They run a targeted Monte Carlo integration just on the order statistic distributions.
Wait, I thought they said Monte Carlo was too slow at high SNRs. Simulating the entire decoder is too slow. But here, they are just using inverse cumulative functions to rapidly generate sets of beta and gamma variables, checking if the boundaries hold, and tallying the results.
Oh, that's brilliant. It's a hyper-focused, breathtakingly fast way to compute a brutally complex probability integral.
It is the mathematical engine that makes their whole order statistics evaluation method actually run on a computer.
Unbelievable. Okay, I'm calling the final completeness check. Have we unpacked every single line
formula, and nuance, from the title to the final appendix.
We have successfully executed the unabridged protocol. Every stone has been turned.
To you, the listener, who has waded through Kaloa fields, Hamming balls, and NP-hard optimizations with us today, thank you. This is what it takes to squeeze 0.2 dB out of the universe.
It's been quite the journey.
It really has. But before we go, I want to leave you with one final provocative thought. Throughout this entire deep dive, we've been hyper-focused on the binary AWGN channel and BCH codes. We are talking about classical electrical systems, voltages, ones and zeros. Right, the world we live in right now.
Exactly. But as we stand on the precipice of the quantum revolution, moving toward quantum communication architectures, the nature of noise fundamentally changes. In a quantum system, errors aren't just bit flips. You have phase flips. You have quantum entanglement decay. You have continuous errors in a completely different dimensional space.
That's a whole new paradigm.
So I want you to mull this over. How might the logic of MCOC, and specifically the concept of prioritizing the least reliable quantum states using something akin to logistic weight order statistics, map onto the delicate error structures of qubits? When a single measurement can collapse the entire state, how do we build the covered space? The math of the future is going to need an entirely new set of paper towels. Until next time.
Welcome back to The Explainer. Today, we are quite literally decoding the noise. We're diving into a genuinely groundbreaking paper from Janz and colleagues at the University of Stuttgart on chase-like decoding. We're going to uncover exactly how digital communication systems correct errors when they're forced to transmit over totally chaotic channels. It's a fascinating read, so let's get right to it. So, you might be wondering, how does a message actually survive a completely chaotic, noisy journey? Think of it like a detective trying to piece together a heavily corrupted letter that's just been dragged through a raging storm. In our digital world, the receiver is that sleuth, and the storm is what we call an AWGN channel, an additive white Gaussian noise channel. To keep things simple, the paper models this as y equals x plus z, right? So x is our perfect original binary signal, and z is the chaotic Gaussian noise just dumped right on top of it. Our receiver gets y and somehow has to guess x. Now, the authors evaluate different ways to solve this using chase-like decoding algorithms. And why chase-like? Well, because when a signal is buried in that much noise, you can't just make one rigid guess. You have to generate a whole list of plausible suspects, which we call test patterns, to find the truth.
Okay, let's dive into this. Here is our roadmap for today. 1. The noisy data problem. 2. Meet the chase decoder. 3. Choosing the right suspects. 4. 3 ways to test. 5. The MCOC solution. And finally, 6. Performance and proof.
Starting with Section 1, the noisy data problem. Let's quickly establish the baseline of digital transmission before we get into the really advanced stuff.
The paper focuses on the absolute workhorse of the industry, binary Bose-Gray Chaudhuri Hocquenghem codes. We're just going to call them BCH codes. These are incredibly efficient error-correcting codes used heavily in data center interconnects and the upcoming Ethernet standards. They're also a massive deal in long-haul optical communication, specifically acting as the component codes for things like OFAC, optical forward error correction. Now, why do BCH codes matter so much? Well, when you're blasting terabits of data under the ocean or across a massive data center, you need a mathematical safety net that doesn't add a ton of latency. BCH codes are that net, and you'll see their parameter set written as NKT. That simply means a code of length n, dimension k, and an error correction capability of t.
The authors point out a pretty massive performance gap right out of the gate. They compare hard decision decoding, where the decoder just makes a rigid black and white guess of 1 or 0, with soft decision decoding. The problem is, if you use a standard bounded distance decoder, or BDD, it only corrects errors up to a very strict mathematical limit. If the noise flips too many bits, a rigid hard decision guess completely loses the message. So to actually survive the noise, we have to use soft input decoders. Soft decision uses the actual analog reliability of the signal. It asks, how sure are we that this signal is a 1 or a 0? By doing that, it keeps our options open. Moving on to Section 2, Meet the Chase Decoder. This is where we actually generate our suspects. The paper explicitly names the Chase2 algorithm as a really common decoder for these soft input scenarios. Let's break down how it works step by step. Step 1, we receive the signal. Step 2, and this is absolutely crucial, we sort the bits by reliability. We look at that soft input and rank the bits from the ones we're most confident about all the way down to the ones that are the absolute shakiest. Step 3, we generate test words by systematically flipping combinations of those least reliable bits. Why? Because the shakiest bits are obviously the most likely suspects for where the noise caused an error. And finally, step 4, we run each of these generated test words through our bounded distance decoder to create a final candidate list, which the math denotes as the letter L. And that brings us to the core metric of the whole paper, the list error rate, or LER. Think of the LER as the detective's absolute worst nightmare. It's the probability that the true culprit isn't even on the suspect list. I mean, no matter how good your final deduction is, if the actual transmitted code word isn't in that final list L, there is zero chance you decode the message correctly. The entire goal of the authors here is to figure out how to generate the absolute best possible suspect list to keep this probability as low as mathematically possible. Section 3. Choosing the right suspects. So how do we actually find these optimal sets without, completely melting our computers? Well, the paper notes that finding the perfect, absolute, optimal set of test patterns belongs to a class of math problems known as maximizing submodular set functions, which is a fancy way of saying it is notoriously NP hard. Testing every single possible error pattern is literally impossible, so the authors outline 3 historical ways people have picked their best hunches. First, you have the standard Chase 2, which tests all combinations in the least reliable positions. Second, there's restricted Chase. Since the odds of a huge number of bits flipping are astronomically low, restricted Chase puts a hard cap on the maximum number of bit flips to save computational power. And finally, they mention logistic weight patterns. This approach ranks patterns by increasing logistic weight, essentially giving a linearly increasing penalty to those less reliable bit positions. Section 4. 3 ways to test. How did the authors actually evaluate the performance of these lists? The authors lay out 3 distinct ways to test how effective these suspect lists actually are, kind of like 3 different magnifying glasses for our detective. Method 1 is order statistics. This is highly complex math, best suited for structured sets like Chase 2, where you can mathematically derive the exact probability of errors. Method 2 is covered space. This calculates overlap probabilities by summing up the space searched by the decoders for totally arbitrary patterns. And method 3 is Monte Carlo. This is your classic brute force system simulation, where you just simulate millions of transmissions and literally count the errors. And here's a direct quote from their conclusion. We have discussed 3 different methods for evaluating the performance of test pattern sets. All 3 give accurate estimations of the list error rate. When they plot the results of all 3 methods on a graph for an extended Hamming code, the lines sit flawlessly on top of each other. By proving that order statistics, covered space math, and Monte Carlo simulations all completely align, the authors have built a rock-solid, undeniable foundation for testing new algorithms. Which brings us to Section 5, the MCO solution. Let's look at maximum covering pattern design. All right, allow me to introduce the star of the show, MCOC, the Maximally Covered Ordered Candidate algorithm. To put it simply, MCOC is just a hyper-efficient detective. Instead of picking suspects based on a rigid rule, MCOC looks at the most likely error patterns and then dynamically crosses overlapping suspects off the list to save time. It iteratively looks at the most probable pattern. If that pattern isn't already covered by the search radius of the tests we've already selected, boom, MCOC adds it to the list. And here's why this is a real game changer. Every time you test a pattern with a bounded distance decoder, it doesn't just check one tiny exact point. The math basically draws a ball or a radius around each test point. Because of this radius, test patterns can naturally overlap. MCOC brilliantly prevents redundant checks. If a highly likely error pattern is already safely inside the radius of a previous test, MCOC literally just skips it. This lets the algorithm totally bypass that NP-hard trap of an exhaustive search we talked about earlier. It beats the computational cost of greedy algorithms, and it still achieves near-optimal results in polynomial time. It's incredibly elegant. Section 6. Performance and proof. Let's look at the actual hard data. The authors reveal that MCOC test pattern sets gain up to 0.2 decibels in block error rate compared to those standard restricted chase patterns. Now I know what you're thinking. 0.2 dB sounds incredibly small, right? But to put that into perspective, you have to look at optical networks. Shaving off 0.2 dB of required signal-to-noise ratio across thousands of kilometers of fiber optic cable or across millions of server connections in a mega data center, that translates to massive, real-world savings in power requirements and hardware costs. It is a highly significant engineering victory for sure. The efficiency here is honestly shocking. The authors tested a specific high-rate 256-239 BCH code, which is standard for optical forward error correction. To hit the required performance threshold, the industry baseline restricted chase setup needs 93 patterns. But look at MCOC. The variable for the number of patterns, Q, equals 42. Just 42 MCOC patterns literally outperform 93 restricted chase patterns. You are getting better error correction while doing less than half the computational work. Even the logistic weight patterns needed 93 to even come close to MCOC.
So we've seen how this incredibly smart heuristic approach to probability, simply asking the algorithm, hey, is this error already covered, can drastically reduce computational load. The question I want to leave you with today is this. As we push toward terabit Ethernet and beyond, how will optimizing algorithmic layers, finding those 42 perfectly placed test patterns instead of 93 redundant ones, shape the latency, the thermal output, and the ultimate power efficiency of the data centers running our future? Thank you so much for diving deep with me today on The Explainer. Keep questioning the noise.
Welcome to The Explainer. So let's jump right into this. Imagine for a second you're sending a critical text message, maybe downloading a massive file, or even just streaming this very explainer. In the literal fraction of a second it takes for that data to travel, it has to survive this incredibly chaotic journey through noisy telecommunication channels. I mean, bits are constantly getting flipped, data's getting corrupted, it's a mess out there. So today, we're diving into a really fascinating paper from researchers at the University of Stuttgart called Chase-like Decoding, Test Pattern Design and Performance Analysis. We're basically going on a quest to explore the cutting-edge math that makes absolutely sure the message you sent is exactly the message received. It's all about the ultimate pursuit of efficiency in data accuracy.
Okay, so to understand how we actually fix these data errors, we really have to start with the foundation. And that foundation is BCH codes, or, get ready for this, binary Bose-Chaudhuri Hocquenghem codes. Yeah, try saying that 3 times fast. These codes are, frankly, the unsung heroes of our modern communication systems. The reason they're used literally everywhere is because they offer this perfect balance. They give us incredibly strong error protection, which engineers refer to having a good minimum distance, while also being incredibly efficient to decode. We're talking about the massive data center interconnects that power the entire internet and those long-haul optical networks stretching across the bottom of the ocean. They essentially add just a tiny bit of calculated redundancy to your data. That way, if a few bits do happen to get scrambled by all that channel noise, the receiver at the other end can still perfectly piece together the original message.
Now, you might be wondering how we actually decode these signals once they arrive. Well, there's a pretty stark contrast between the 2 main methods. First, you've got hard decision decoding. And it's exactly what it sounds like, rigid. The receiver gets a signal, looks at it, and basically forces a choice. Is this a 1 or a 0? Boom. Hard, final choice. It's super simple, sure, but it leaves a massive gap in performance because you're throwing away so much useful contextual information. But then we have soft input decoding, and honestly, this is where the magic really happens. Instead of just stubbornly picking a 1 or a 0, the receiver asks itself, okay, how confident am I that this is actually a 1 or a 0? It uses these confidence levels, which we call reliabilities, to make much smarter, far more flexible decisions, and that dramatically improves performance. So moving from hard to soft in decoding is literally a quest for better, faster, more accurate performance.
So here is our roadmap for today. We'll cover the error correction problem, chase-like decoding, measuring list error rate, designing better patterns, the MCOC algorithm, and finally, the performance results. Let's get to it.
Section 1. The error correction problem and noise in the channel. All right, so when bits, those tiny 1s and 0s, travel over a channel, they get hit by something engineers call additive white Gaussian noise. Think of it like trying to have a deeply complex conversation in a crowded, unbelievably loud room. The noise physically alters the signal, so a really strong 1 might arrive at the destination looking suspiciously like a 0. To solve this, we use the incredibly famous Chase-U2 algorithm. Let's walk through how this works. First, the algorithm receives the noisy vector and makes an initial, hard decision, just a baseline guess. But then it does something really clever. It looks closely at the bits it's least confident about, the ones with the lowest reliabilities. And it just starts flipping those specific shaky bits, generating a whole set of what we call test patterns. It's essentially smart guessing. It's asking, okay, if I was completely wrong about this one weird bit, what would the message look like? It decodes all these different variations and creates a candidate list of potential original messages. The ultimate goal here? Just making absolutely sure the true, correct message is somewhere on that final list.
Moving on to Section 2, measuring the list error rate, or our 3 rulers.
Now, if the entire point of the Chase algorithm is to make sure the correct message lands on that candidate list, how do we actually know if we're doing a good job, right? We have to measure something called the list error rate, or LER. That's simply the probability that the true sent code word is totally missing from our generated list. To make sure they were being extremely accurate, the researchers didn't just rely on one single method. They actually used 3 completely distinct mathematical rulers to measure this list error rate. First, they used order statistics, which is fantastic for patterns that have a very specific mathematical structure. Second, covered space probability, which calculates the total probability space searched by the decoder. And third, Monte Carlo Simulation, which is basically running a massive brute force simulation of the entire transmission system. And here's the absolutely crucial takeaway. All 3 of these totally different methods perfectly align. They give equivalent results, which absolutely proves that the foundation of this study is rock solid.
Section 3. The search for better test patterns. Okay, so we know the Chase algorithm makes its educated guesses by flipping the least reliable bits, but testing literally every single possible combination of flipped bits, that takes way too much computing power. It's just not feasible. So engineers usually use subsets of patterns like restricted chase or newer logistic weight patterns. But the big question the researchers asked was, is there a better, fundamentally more efficient set out there? Well, here is the massive mathematical roadblock they ran into. Finding the absolute optimal set of test patterns belongs to a class of problems called maximizing submodular set functions, and it's acknowledged to be NP-hard. Now, if you're not in computer science, NP-hard basically means it is practically impossible to solve perfectly in any reasonable amount of time. Doing an exhaustive search to find the mathematically perfect set of guessing patterns would literally take forever. They couldn't brute force it. They desperately needed a clever workaround.
Which brings us to Section 4, the MCOC breakthrough, the Maximally Covered Ordered Candidate.
Enter the MCOC algorithm. I am genuinely so excited to share this part with you, because they couldn't just calculate the perfect set of patterns. Thanks to that pesky NP-hard roadblock, the researchers invented a brilliant heuristic design rule. They called it Maximally Covered Ordered Candidate, or MCOC for short. Instead of just blindly generating guesses, MCOC acts like a highly efficient net. It systematically looks at the most probable error vectors first. Then it pauses and checks. Wait, have my current test patterns already caught this specific error? If the answer is yes, it just skips it, doesn't waste the time. If the answer is no, it generates a brand new pattern specifically designed to cover it. The logic is just so elegant. It guarantees that it covers the absolute maximum number of likely errors without wasting a single ounce of computational power on redundant, overlapping guesses.
And finally, Section 5, Performance and Results, a real victory for efficiency.
So the elegant theory sounds great, but does it actually work in practice? Let's look at the hard data. The researchers found that test pattern sets designed using their MCOC algorithm gained up to 0.2 decibels in terms of block error rate for high-rate BCH codes, especially when compared to the commonly used restricted chase patterns. Now, 0.2 decibels might sound like a tiny drop in the bucket, but trust me, it is huge. In the cutthroat world of massive data centers and global optical networks, engineers are literally fighting tooth and nail for every single tenth of a decibel. Achieving a 0.2 dB gain? That directly translates to massive, real-world savings in both latency and power consumption across the entire global network.
And the numbers regarding pattern usage are honestly the real mic drop of the entire paper. Let's look at a specific extended BCH code used heavily in advanced optical communications. Just to achieve the baseline required error correction threshold, the standard restricted chase algorithm needs 93 completely different test patterns. 93. Now look at MCOC. It achieves superior error correction using only 42 patterns. 42! That is less than a half. It's a staggering leap in efficiency. Practically speaking, it means the decoder is doing way less work, it's burning less energy, and it's operating significantly faster, all while actually providing better data accuracy. It's a total win-win.
Which really leaves us with this final, incredibly important thought. We are constantly pushing the extreme boundaries of data transmission, right? We're hurtling toward 400G and 800G Ethernet standards. But the physical limitations of the cables and the hardware can only take us so far. It's algorithmic breakthroughs, exactly like MCOC, finding these ingenious ways to work smarter, not harder, on a purely mathematical level that will actually enable the speed of our global future. As we move toward those next-generation Ethernet standards, how will these hidden, microscopic, algorithmic efficiencies shape the next entirely new decade of human connectivity? It is absolutely something to keep an eye on.
Thanks so much for joining me on this explainer, and keep learning.
Okay, welcome back to The Explainer. Today, we are unpacking something pretty amazing from the Institute of Telecommunications at the University of Stuttgart, and it's fundamentally about making our entire digital world faster, way more reliable, and just incredibly efficient. We're going to be looking at a new algorithm for optimizing digital communication, specifically diving into something called chase-like decoding, and this major breakthrough pattern design known as MCOC. If you've ever actually stopped and wondered how your data somehow survives its chaotic, globe-trotting journey without turning into total gibberish by the time it reaches your screen, well, you are in exactly the right place. I'm absolutely thrilled to guide you through this one, so let's just jump right in.
Right, so here's our quick roadmap for today. We'll start with a digital noise problem, then look at hard versus soft decoding, meet the chase decoding detective, explore 3 ways to test this, introduce a smarter guessing game, and finally, look at the actual performance payoff. All right, part 1, the digital noise problem.
So first up, let's talk about the literal, invisible war that is going on inside our digital cables every single second of the day. I want you to imagine every text message you send, every 4K streaming video, every bank transaction, just fighting its way through a massive storm. In engineering, we call this additive white Gaussian noise. See, your clean, pristine ones and zeros are sent out, but the channel they travel through just dumps random interference all over them. By the time the data reaches the other side, it's a mess. Some ones look like zeros, some zeros look like ones. So how on earth does your data actually survive this without getting completely corrupted?
Well, the answer lies in mathematical armor. Specifically, something called BCC codes, or binary Bose-Chaudhuri Hocquenghem codes. You absolutely do not need to memorize that name. Just know that these codes are our frontline defense. They're heavily used in massive data center interconnects and those super long-haul optical networks. They act almost like a protective shell around your data, effectively sniffing out and repairing those corrupted bits as they arrive. But to actually fix those bits, the receiving end needs a solid strategy to read them first.
Which brings us to part 2, hard versus soft decoding.
So, how do we actually decide if a messy, distorted signal is a 1 or a 0? Well, we basically have 2 main approaches here. First, hard decision decoding. It's incredibly fast, but man, is it rigid. It looks at a signal and just immediately snaps it to a 1 or a 0. The problem? Doing that throws away a ton of subtle clues, leaving a huge performance gap compared to what's theoretically possible. On the flip side, we have soft input decoding. This one's flexible. It looks at a bit and says, I'm about 90% sure this is a 1, but I'm only like 51% sure about this other bit over here. It brilliantly uses these reliability metrics, making it highly accurate. But, and it's a big but, it is computationally exhausting.
Moving to part 3, the chase decoding detective. So to bridge this exact gap between blinding speed and high accuracy, we use an established solution called chase-like algorithms. Honestly, you can think of the chase-like decoder as a highly methodical detective. When it gets messy data, it doesn't just guess blindly. No. First, it identifies the least reliable bits, the ones it's the most suspicious of. Then, it generates test patterns by strategically flipping those doubtful bits to create a sort of lineup of likely suspects. Finally, it decodes these patterns to see which one makes the most mathematical sense. It's literally like trying to crack a combination padlock by only testing the numbers that feel a little bit loose.
Now, up until this new research, we've basically relied on a few standard sets of these test patterns to guess where the errors might be hiding. The big ones are chase 2, restricted chase, and logistic weight patterns. And look, they work pretty well. But the researchers behind this paper asked a crucial question. Can we guess better? Can we somehow find that right combination faster?
Let's look at part 4, 3 ways to test.
Before we jump into their big solution, we really need to look at how they actually measured the performance of these guessing strategies to make sure their findings were completely bulletproof. The holy grail metric here is the list error rate, or LER. Basically, what is the chance that the actual right answer wasn't even on our detective's list of suspects? The researchers rigorously proved their findings using 3 totally distinct methods. They used order statistics for the hardcore mathematical modeling, covered space probability to see how much of the metaphorical room they actually searched, and finally, direct Monte Carlo simulations, literally just running data through a simulated noisy channel over and over again. By getting all 3 of these totally different methods to agree, they proved their evaluation was incredibly accurate.
All right, part 5, a smarter guessing game.
Okay, so with their testing methods locked in, the authors introduced their primary breakthrough, the real game changer in optimizing this whole system. Enter MCOC. That stands for Maximally Covered Ordered Candidate. Instead of using those traditional, somewhat rigid test patterns we just talked about, MCOC plays the guessing game so much smarter. It dynamically prioritizes the highest probability errors based on their distance. It essentially pauses and asks, okay, what is the absolute most likely error that just happened, which we haven't already checked? By covering the most likely errors first, it wastes absolutely zero time checking highly unlikely bit flips.
And finally, part 6, the performance payoff. So, the million-dollar question. What actually happens when you replace the old guessing patterns with this hyper-efficient MCOC algorithm? Well, to hit the exact same target performance for a high-rate extended BCH code, the traditional restricted chase method requires the system to check 93 different test patterns. MCOC? It only needs 42. That is literally less than half the computational work to get the exact same or even better results. It cuts the processing burden dramatically, which, as you can imagine, is just a massive win for high-speed networks, where literally every single microsecond counts.
But wait, it actually gets better. This efficiency translates into an impressive 0.2 decibel gain in block error rate compared to the old commonly used patterns. Now, in the world of telecommunications and signal processing, getting a 0.2 dB gain without having to bolt on heavier, more complex hardware, that is huge. It essentially means you can push your data further or faster using less power entirely because your algorithm is just plain smarter.
This quote right from the source material really hits the nail on the head. It drives home the significance of working smarter, not harder. By simply redesigning the basic order and logic of how we test for errors, by essentially training a better detective, we can completely outperform systems that are out there doing twice as much computational heavy lifting. Which leaves us with this final thought to chew on. As our global data needs absolute skyrocket, we're talking AI, 8K video, massive cloud infrastructure, we can't always just throw more raw physical power at the problem. We desperately need these smarter, invisible algorithms like MSCOC, working behind the scenes to keep the digital world running smoothly. So think about that the next time a heavy web page loads instantly for you. There's a brilliant, highly optimized guessing game happening at the speed of light to make sure every single bit is perfectly in its place. Thanks so much for joining me for this explainer, and definitely keep your curiosity alive.